Okay, welcome to Kernel Debug Stories. I'm just going to leave it 30 seconds maybe, just to make sure that I've got everybody ticked over to 9 o'clock on their clocks rather than just mine, and then we will kick off. Okay, so like I say, welcome to today's webinar. Just a couple of very small logistical things. Normally there's a section here about turning your cameras off, but because we have such a large crowd today, we're running it so that you can't turn your cameras on anyway, so I don't have to warn you about anything like that. Questions are certainly welcome. I've got the chat and the Q&A box open to the left of me, just next to me here. And there we have a moderator on the call as well, in case I have connection trouble or anything else. They can also see the questions and remind me if I've missed something. We have slides and downloadables if you want to take part in the lab activity after the webinar. So the links here, I don't expect you to be able to type that in dead shot while it's still on the screen, but we will have it in the chat very shortly. And that should help you find slides and things to follow as we go. I'm also going to kick off with a very short biography. This is not really because I especially enjoy telling you all about my history, but it allows you to have a think about my own prejudices. You know, in the simplest way to put it, you know, if you have a server and your software breaks, you assume it's the software's fault. If you're an embedded developer and the software breaks, you tend to blame the hardware until somebody can convince you otherwise, which is not a good mindset, but it's quite common. Okay, so yeah, I started my career at ST Microelectronics, where I joined a toolset team. And at that point in the, this was the late 20th century, at that point, toolsets came with real-time operating systems built into them. It was before Linux was heavily used in the embedded world. And then as the set-top box industry pivoted from custom RTOS to GNU Linux, I moved along with it. So this would have been about the 2002, 2003 point when GNU Linux was starting to make significant inroads. That's when I started to take part in GNU Linux development. And during the following years, ST made set-top boxes in the division I was in, and I ended up working in more or less every bit of set-top box software over the next 10, 11 years, and with the possible exception of security. So I have done kind of networking, audio-video codecs, and back in the toolset days, everything from C libraries upwards, right the way up to software architecture towards the end of this process. For my final years at ST, I was a tech lead that came in to try and bring an ST driver stack project back on track. It wasn't wandering afar, but that's when I came in, and it was that point that my role first became largely consultative. That it was a very, very big group, and I was much more involved in supporting and helping those team members to be productive than I was to actually develop anything myself. And that switching to consultative role led, among other things, to my interest in kind of training and mentoring activities like that. And it's probably the first reason I ended up talking to you today. I joined Lenara in 2014. I spent a year in the Kernel working group, working on debugger technology, and then as a tech lead for the support and solutions engineering team. I tend to gravitate towards generalized roles, you know, rather than deep specific focus in one area. So that means I have a role at Lenara now, which is very varied, but it's all centered around that background I have in tools and operating systems. So whether I'm leading the support team, whether I'm the training manager, or whether I'm the upstream KGEB maintainer, it's all kind of links back to that heritage that I have in tools and operating systems. Okay, so that's left a little bit of time for everybody else to arrive. So we'll now get into the course proper. So quick introduction is that The Linux kernel provides enormous numbers of tools to help us to debug it. Every single one of those tools could and usually has been the subject for a full hour in a conference schedule. I'm going to cover a lot of those tools, and I only have 2 hours or so to do it. We've booked into 2.5 hours because there's so many of them, it does tend to overrun slightly, which is why you've got 2.5 hour invite. And we have to do tricks, of course. We have to do tricks to cover so many tools in so much space. And the main trick we do is we will focus on when to use the tool rather than how to use it. So we'll present you with stories that represent sort of simplified use cases of potential debugging challenges, and then we'll introduce the various tools that we could think of that could be brought to bear to address them. And that means that at the end of today, you'll have covered a broad spectrum of tools. And in the case of this webinar, that's providing you a springboard for further study. You can find the tools that are going to be best fit for you. And then you can either go and learn about them or find somebody to talk about them more. Okay, so I'm going to start with what I call the basics. It's not really the basics, more kind of the fundamental starting point that we come to from debugging. So the first thing I want to bring up is the sort of debugging beyond the debugger. I am the KGDB maintainer. A KGDB maintainer. I do believe that Stop the World debuggers are tremendously important and useful tools, but I'm not going to talk about them today, because I hope that for most people with experience developing software, when you say a debugger, the thing that comes first to mind is that traditional Stop the World debugger that can stop and step and examine data. So what else have we got? The other kind of pillars, if you like, I think of as tracing. So tracing is the process of gathering events during system execution into some kind of log and allowing you to see in time the behavior of the system. Tracing is much more effective when you have timestamps, so that you can understand what's happened in the passage of time between messages. And just to really put this into perspective, printk is a form of tracing. Printf debugging is a form of trace-based debugging. It's a trace-based debugging where you don't have very many tools to help you. You've just got your eyeballs and a text editor. But ultimately, printk is a tracing tool. There are other tracing tools that can be brought to bear. There are ways you can gather more tracing events by attaching to data sources where somebody hasn't thought to write a printk. But printk is itself a form of tracing debugging. The second option is profiling. So profiling usually comes up in performance analysis, and it's quite often attached to similar data points that you can have with tracing. But instead of gathering a list of events, you crunch that information down to statistics about system execution. So you can be looking for threads that are dominating the CPU. You can be looking for the place where you most frequently miss one of the caches. Profiling and tracing have a lot in common, to the extent that you can actually process trace files to generate profiles retrospectively in some cases. It depends how the tracing has been gathered. What quite often distinguishes profiling is it's based on periodic interrupts and examination of the state of the system. So you can have a periodic interrupt, you can trace the periodic interrupt, and from that you can derive a profile, for example. The final pillar is this stop the world or post-mortem debugging. So I view as things like KGDB and classic debuggers to be stop the world debuggers. You stop the world, you examine the data, you set them running again. Post-mortem is simply a special case of stop the world where you don't have any intent to continue. And post-mortem I find to be the dominant model I would use when debugging the kernel, because quite often I've been involved in real-time systems, and as soon as you stop the kernel, when you start it again, what you basically see is all the error handling fire because you've missed all your deadlines. It's a useful test to be able to miss all your deadlines, start and recover. It shows that your real-time recovery processes are working. But other than that, I don't really expect to be able to start the world again. So I'm looking for a way to stop the world and examine the data, but not necessarily to start the world again. I do view combinations as enormously powerful, and the most intuitive one is that if you have trace logs that are running, particularly if they're not attached to any kind of print, they're just logging into memory somewhere, and then you can arrange for a breakpoint to fire shortly after something bad has happened, the thing that you're trying to debug has reproduced. If you can arrange the breakpoint very shortly after that in your stop the world debugger, you can then use the trace logs to help you interpret the state of the memory. So anyway, that's the kind of philosophy we have about these towers. And like I say, we're not going to talk about stop the world very much, except where it's automatable. So we can either capture the post-mortem automatically, or we can gather an oops trace. So oops traces, the stuff that comes out to console when something's gone wrong, is a form of automated stop the world analysis. That oops trace is basically running into a trap handler. It's gathering information about the system that can be useful to debug the system. It dumps that information to the logs, and then it either panics or it kills the process depending on when we've had our problem. So we've got an alarm going off outside my house. I'm just going to close the window. So yeah, those are the three towers we could look at. There is a third thing I like to bring up at this point, and it's based on that combination being powerful. If you can find when something has gone wrong early and stop the world, you can then look back in the traces. And this is failing early, I think we can call it. So failing early basically means trying to bring the system into some kind of debuggable state as early as possible after the fault has manifested itself. There are several reasons for this. I mean, firstly is that many of the trace tools we use, including PrintK, are based on circular buffers. So if you allow the system to continue past the point of failure, there is a chance that your evidence will have been evicted. The evidence that actually told you how the bug has manifested itself could be evicted. Bugs also intrinsically can damage the system, particularly kernel bugs. So if you can fail when the system is still alive enough to be analyzed, that's a really good thing. So one of the characteristics of most kernel debugging is we tend to rely on self-hosted tools, which means the tools we are using to try and debug the kernel are running as part of the kernel. That means that if you have certain types of memory corruption and so on, you can do enough damage to the system that the self-hosted tools no longer run correctly. So again, if we could bring the system to halt when we have first order effects, we have a much better shot at allowing our self-hosted debug tools to do their job. Excuse me. The other thing about detecting true symptoms is the thing you actually see that comes in your bug report or you're analyzing from your test suite, whatever it is, may be a second order effect. It may be that something has gone wrong, and in going wrong, it has caused a second problem. You see this quite often when people report problems. They put the last 10 lines of the kernel log and say, what went wrong? And they show you something failing at the end. And your first response would always be, send me the whole kernel log, because you're usually interested in the first error, not the last error. And finally, failing early, trace data can be enormous, particularly if you're running tools like ftrace, which we'll talk about later. They generate an enormous volume of trace data, and having a little flag in that trace data that says, within this 10 millisecond window prior to this flag, this is where the error is just valuable to be able to navigate that enormous quantity of trace information. So this is why we do it. Many of the tools in things like the kernel hacking menu are actually mechanisms to automate failing early. So if you figure that you need to have some kind of fail early to help you understand the problem, the first thing we can do is bring in existing triggers to try and spot it. Most of these failing early Linux debug tools are based on reporting the errors via PrintK, and PrintK is extremely defensively coded. I mean, it doesn't fail easy. It is a self-hosted tool, but it is quite rare to have bugs other than kernel, other than things that kind of lock up the bus, that leave code executing and don't allow messages to come out. If the kernel is running and it calls printk, there's a, it's very, very hard to prevent that message coming out. You can do it. There are ways you can damage the system so it becomes impossible to printk, but it can be difficult, with the possible exception of working on serial drivers, because they're where the message comes out. Once you've got printk, git grep makes it fairly easy to map a printk to the corresponding source code. So even if you don't fully understand how the trigger works, if you can't figure it out from the logs, you can actually map back to printk messages to find out what's going on. So in a moment, I'm going to talk about some of the existing fail early tools, but what happens if they aren't fit for you, if they don't help you spot the problem that you have? And this is the final thing that I like to bring up when we're talking about failing early, is can you write a recognizer? You've done some debugging, you've got some idea of what is going wrong, but you need to be able to get in a little bit earlier and figure out what's going on. It's all of this trying to get back to the actual point of failure, is can you recognize the symptoms of your bug in code? If it's a corruption, if it's this value is gone out of spec, whatever it is, can you put in something that says, is this value currently in spec? If not, breakpoint. And then the ultimate the step is that you can then sprinkle that recognizer over different places within your code base, looking for the earliest point that it changed. So this is where you effectively have a potentially second order effect. Something's changed value, and you're trying to figure out where it came from. So yes, ideally you develop your recognizer eventually to spot first order symptoms, although you can work on recognizers that work on second order symptoms to try and figure out what the first order effect was. It's also very useful, as I said, to be able to reason about the time window in which the system was damaged. So it's not just that it has failed that is the really important information, it's that it has failed and n milliseconds ago it hadn't failed, because you know that you ran the recognizer n milliseconds ago as well. So even if you can't bring to bear the existing Linux debug tools, that doesn't mean that the fail early concept is inappropriate. It means that you have to write your own recognizer. So just to talk about some of the recognizers you don't have to write. These are some of the common techniques. I can't possibly show you the whole kernel hacking menu, but these are some that sprang to our mind when we were discussing this. So first off, we have things that can look for problems with stack overflow. So Linux kernel stacks are actually surprisingly small. They're either 4 or 8K, and if you overrun them, bad things can happen. I'll actually jump to the bottom, because for people with ARMA64 systems, this VMAP stack is without doubt the most powerful of the techniques. If you enable VMAP stack, which is I think actually in general rather than kernel hacking, it will allocate the stacks from virtual memory rather than from the big pages that map the whole of kernel memory. So when you have the kernel, the way it handles memory is the bottom n gigabytes of RAM tends to be mapped one-to-one with massive pages, because it allows you to access the physical memory very, very quickly. But there is then a virtual memory area where the kernel can allocate pages and linearize them using the MMU. And once you're in that area, you can place stacks there, and you can arrange for guard pages to be unallocated between the stacks. So in other words, if you run past the end of your stack, if you overflow it, the MMU will fault immediately. And that's a very, very powerful way to get to the exact point when a stack overflows, and also allows you to be very confident when a stack doesn't overflow, because you're guaranteed to find it. If you do not have VMAP stack, which can either be because it's not implemented, I'm not sure that it's implemented on 32-bit ARM systems, because 32-bit systems tend to be starved for address space, because I've only got 32 bits. And because they're starved from address space, you don't want to waste that allocating kernel stacks everywhere in the precious virtual map space. So there are some other mechanisms. You have shed stack end check, which is simply a mechanism that places a marker at the limit of the stack. And the theory is that that marker would be overwritten if the stack overruns. And then it checks for that marker and that it's still present when a task deschedules. So in other words, when you stop executing this task, you can discover that it's already done some corruption, roughly speaking. So this one is a good example of why VMAP stack is much better, because it fails at the first moment before any secondary corruption happens. Whereas this middle one, the shed stack end check, can't prevent the stack overrunning, but it can detect that it has previously overrun and tell you which task it was that overrun. And then you'd have to look back to some other kind of tracing technique to find out what actually happened. And then just working back from that, we have this is actually technically a static analyzer rather than a fail early. Frame warn is basically a compile time check to spot large stack frames. If you accidentally allocate a massive array on the stack, more than a K, I think it is by default, frame warn will reach in and tell you about it. So this is run very frequently over the main kernel, but particularly if you have vendor kernels, it might be worth turning this on and make sure that there aren't any vendor code in the kernel that has allocated very large buffers. So once you have your stacks nice and robust, we might want to think about things like memory debugging. So memory debugging, we'll start off with talking about poisoning. So poisoning is usually a mechanism of effectively doing a big mem set over memory buffers so that they have particular recognizable values. So the simplest ones are when you free a buffer, you fill it with a poison pattern to show that it's free. When you allocate it, you fill it with a particular poison pattern to show that it is undefined. And then if you see either of those patterns in your registers or in your stack traces, you can be reasonably confident that you've had some kind of memory management mistake. Slub debug does much more than that as well. It can do certain types of automatic debug detection, spotting certain corruptions within its own data structures so that it can try and find things back. It can mark who allocated it to help you find leaks. It can even do tracing to help you observe every allocation and deallocation of the system in a tracing form. One thing to mention about slug debug is there is an option, config slug debug, that you can turn off, but it's really there. It was slug when it was introduced had debugging options on all the time. It was designed to be performant with slug debug enabled. Slug debug was added to allow you to shrink the system down to really, really tiny memory profiles, which are, they still exist, but they are pretty rare, and classic modern embedded systems that do multimedia or anything like that have more than enough memory to leave slug debug enabled anyway. So so this is slug debug is a good tool because it is potentially going to be enabled all the time, rather than something you have to reach in to the kernel and rebuild it. Debug page alloc is essentially equivalent to vmem stack. It's able to observe access to free pages. This works by taking those huge pages that I mentioned and actually making them into small pages instead, so that the whole of the kernel physical memory is now allocated using 4K pages, or represented using 4K pages in the page tables, and that allows you to ban access to certain of those pages. So debug page alloc arranges for free pages to be inaccessible to the kernel, and therefore if you accidentally go past a buffer and hit those pages, you'll get an MMU fault. And then for places where you can't use MMU to help us, we have page poisoning, which is simply filling empty pages with poison patterns and then validating when you reallocate that they're still in place. And then finally, we'll talk about lock debugging. So the other big thing that is going to happen in code with bugs in tends to be problems with locks. Over many years, Linux has progressed to a very fine-grained locking approach because it's more performant. And as you go down to fine-grained locking, it tends to be a challenge for most humans to track the locking interactions fully. So we look towards automated tools to help us do that correctly. So there's some basic things like debug mutexes, which are actually just sanity tests to make sure you're not abusing the mutex API. In particular, it is not to use a mutex as a mutually exclusive primitive. It follows that when you release a mutex, you must be the process that locked it. It's not like semaphores, where it can be correct to take a semaphore in one thread and release it in the other. That's never the right thing to do with mutexes. So those kind of sanity tests, make sure that hasn't been done. The one that has the biggest bang for buck is probably debug atomic sleep. This verifies that you haven't called a sleeping lock of any form, whilst you hold additional spin locks and things like that, that mean that it's unsafe to take a sleeping lock. When you own a spin lock, it is unsafe to take a sleeping lock. So whenever you take a spin lock, when you've got debug atomic sleep enabled, those are being recorded so that you can yell about it if you try to sleep while taking it. There's also things like debug lock allocation. So one of the most difficult things with locks to debug, usually straight lock debugging, there's lots of tools that can apply to it. But if you try and lock a lock that has already been freed, so if others, you've got the memory, you've deallocated the lock, but somebody is using it after free, it's a particularly nasty one because it has effects on other threads, so you can't see what's going on because they get stuck. So debug lock alloc is effectively a memory debugger, but specifically focused on making sure that we don't use locks after free because it's some of the hardest bits to debug. I will mention the lockup detector. So the lockup detector comes in two forms. Firstly, you have a high resolution timer IRQ that is used to make sure that the tasks are scheduling correctly, they're not stuck. There'll be a soft lockup that prevents the scheduler from running for some reason. You can also use NMIs, non-maskable interrupts, to monitor the HR timer IRQ to make sure the IRQ system is still working as well. I've got that printed as non-ARM systems at the moment. As it happens, ARM64 has got a pseudo NMI these days. There are patches around that can bring the lockup detector to ARM64 systems. But it is not there by default in the main kernel. Yes, I will get to Wiki's question when I've got to the bottom of this slide. So the final thing is RCU stall detection. RCU stall detection is not actually a debugging technique, or at least it's not a debugging tool. Read copy update is a alternative to locking within the kernel. It allows you to read data structures without locking and hit various rendezvous points where it becomes safe to update those data structures. So it's very much designed to have read optimized performance for shared data structures. In order to have that, you have to be able to read the update section frequently enough. So basically what happens when you do read copy update is you have a data structure that you're reading from. If you need to modify it, you make a copy, which is just a read, until you have a shadow copy of the data structure, which you update. And then at some point, you've got to switch from using one version of the data structure to the other, which is this safe rendezvous point. And RCU stall detection basically tells the system that we're not able to reach the rendezvous point from all CPUs. And the reason that is helpful is because if on an SMP system, one of the cores has got stuck, RCU stall detection will tend to trigger. So it's really, really helpful in letting you know that one of the CPUs has stalled. It is also very unhelpful because the stalled CPU we cannot get a stack trace from because we cannot get it to do anything for us. So it is very useful for reasoning. If you see RCU stall detection, it's very, very likely that one of the SMP cores has locked up. You will then have to reach one of the other failing early techniques to try and figure out where or how it is locked up. So there's a question in the chat about which of these tools and techniques are available when you cannot rebuild the kernel. That's a very difficult one. So most of these, in fact, it will come up when we talk about levels of intrusion. But most of these have a cost. Most of these will cause your phone to suffer slightly in benchmarking tests. So almost all of the kind of memory debugging, lock debugging things are likely to be turned off when you are on a production embedded system. There's two other aspects to this that we could add when we're talking about which of these tools and techniques are still available. The first is obviously distros. If you are not a dyed-in-the-wool embedded developer, then there is a fair amount of tracing technology turned on in most distro kernels. It tends not to have these on, again, because they hurt the performance and benchmarking capabilities. But some of the other techniques, tracing, trace points, some other things we'll look at later in today's talk, are available. And that also goes to Android phones as well. So Android sits in an interesting space because you can load your own apps on it. It's used as an app development platform. So you do need to have enough debug capabilities, not just to debug the user-based applications, but to understand how much they're costing the kernel to do it. So again, for that reason, Android phones will tend not to have failing early techniques enabled, but they will have certain debug technologies enabled. Things like trace points and F-trace infrastructure are enabled, even if function tracing is not. So I think the philosophy we describe with Android is it's allowing you to trace things where you've got trace points, somebody intended it to be traceable there. It doesn't have general purpose function tracing that could be used to study things in a bit more detail than they might like. There's a comment here about no KLSR. Yeah, we will discuss that very briefly when we talk about, in fact, let's cover in the lab sessions. It's more than just no KSLR, because modern kernels are actually designed to suppress memory addresses going out in the kernel log anyway. So I personally view no KLSR as something that I care about with response to things like KGDB and stop the world symbolic debuggers. So if you randomize the address space, kernel address space layout randomization, if you randomize the kernel layout, then it becomes more difficult to map kernel debug information, stuff in the dwarf, and look up symbol names. So if you're not doing debugging, so none of the things on this screen here will result in you having to do very much symbol lookup yourself, because whenever the kernel prints a stack trace, it does the symbol lookup, and it's already coped with the fact the address space layout was changed. When you want to use external tools like GDB, you either have to teach it how to adapt to the kernel addresses, or you have to turn off address space layout randomization. So yes, debugging, it's definitely an application to turn it off. But in terms of print K memory addresses, modern kernels are actually suppressing all printing of addresses, regardless of whether you've got address space layout randomization or not. They actually print a hashed version of the address. So it's important to talk about level of intrusion. Once we've talked about these debug tools, and I've told you that most of them are turned off by default because they have an overhead, we have to think about that overhead. Most of the ones I've shown you are quite comfortable to be turned on for experimental purposes. Sorry, I'm just looking at the question that's come up. High resolution timer cannot sleep, but some exported functions from kernel use mutex. How to? I think you'll have to expand that question. I can't work out how to map that to the topics I've been talking about. It's certainly true you can't sleep from any interrupt handler, just as you can't sleep on your own spin locks. So yes, levels of intrusion. So some of these techniques will use significant quantities of CPU or memory. It will depend on the nature of the tool. So the most powerful tools are both enormously powerful. They can detect things that are tremendously difficult to detect with other mechanisms, but they also have a significant performance cost. Others are uneven in their performance. So taking the example of poisoning, for example, which we've got at the bottom, poisoning does not affect the general behavior of or performance of the kernel. It only hits patterns where you're doing significant amounts of memory allocation or deallocation. Now, that is a fairly normal thing for the kernel to be doing, to allocate and deallocate memory. So it will still do it in certain important paths, but it will be lumpy. It will hit some paths where we're doing allocation a lot. The rest of the time it's uninvolved. It's not there at all. It has to be acknowledged when we're talking about intrusion that there are going to be bugs where even small instrumentation changes can alter or prevent reproduction. Classically, these are called Heisenbugs. They exist. There's nothing you can do about them. Once you've turned on tools to try and find things, you may not be able to reproduce your problem anymore, or it may take longer to reproduce. But in exchange for that, they're sufficiently powerful that if they do find the bug, you found it fairly quickly. So there are always going to be cases where you have to turn off some of these advanced debug technologies because they stop the bug manifesting. And you either have to do careful targeted instrumentation yourself, or in the worst cases, these can go on for a long period of time. If you're trying to add instrumentation, every time you add instrumentation, the bug goes away. Yeah, there's not much advice I can offer there, except you just have to keep plugging away at it. More significantly, if you're an embedded developer, some of these tools are so expensive that you actually cannot deploy them on your low resource embedded system. So you can reason about what the tool is designed to detect and whether it's likely to be useful. And in particular, you might choose to do a partially integrated system. So while you might not have enough resources to pull up the full set of use cases for the system, you might be able to run subsystem or unit tests in order to free up the resources needed to run the tool. And just to give you a sense of the scale of things, I've mentioned poisoning. That's not too expensive, except on allocation intensive workflows where it becomes extremely expensive because of the memory costs of writing stuff. So another one is prove locking, which we'll talk about in a minute. This is a debugging tool to try and observe when there is a risk of deadlock due to a deadly embrace between locks taken in different orders. It is tremendously powerful. It can bring out locking problems that are really hard for humans to reason about. And that has costs. When you take a lock, we've got to check the whole stack and verify that the lock stack has been seen before. And if it's not been seen before, we have to do some analysis to work out if the locking sequence was safe or not. Kernel address space sanitizer, address sanitizer is a compiler assisted debug mechanism where the compiler will instrument every single memory access, and there will be a validity check at runtime to verify if you're allowed to read or write to that particular address on a byte by byte basis. So that can find almost every conceivable scribble within the system, because we're able to instrument every single memory access, and we can go into very fine grains. We don't have to worry about page allocations because we can go into below page stuff. We can detect reads of undefined memory. It's tremendously powerful. But you have to commit 1/8 of your available memory to hold the data structure that decides which part of the actual memory is valid. Heaps become less RAM efficient because we've got to allocate little gaps between them so we can trigger the address space failures. And the kernel overall, with all that instrumentation, will run about 3 times slower than normal. There is also a hardware-assisted version of kernel address space sanitizer that we'll look at in a moment, but again, that has an overhead. So these are expensive tools, but they are very, very powerful, so they pay off for us. So I'll go back to this question. It's saying, if we have a mutex mailbox protocol protected by mutex cannot be shared in per CPU handlers. So that should, I mean, if you're talking about how do I detect the problem, debug atomic sleep should be finding this sort of thing. if you're talking about how do I know if it's safe to make a call, you either have to read the documentation or study the call. Okay, so rolling back onto these last couple of things, I just wanted to look at the different kind of fail early techniques that are expensive and give you more of a sense of what they do. So the idea behind prove locking is that if you have two pieces of code which could run in different threads, where we have different locking orders. In this case, we've locked the subsystem and then the driver. And this incidentally, the reason I've called them subsystem and drivers, because this is one of the most common patterns and ways this has happened, is because you have a subsystem lock and a driver lock. And during, say, one operation, when you're being called by the subsystem system takes a lock, then you go into the driver code and the driver takes a lock. And then you have this other thing where you're an interrupt handler, and now the interrupt handler takes a lock, and then you call it a subsystem, the subsystem takes a lock, that can deadlock. Quite often the timing windows for these deadlocks is small. Instantly, you won't see them right next to each other. There's a big function stack between these actions. I'm just showing the locking sequences here. Timing window is very small, so it's unlikely you'll find this during simple development. You won't necessarily see these kind of deadlocks. It's much more likely that problems of this nature are going to be discovered during final QA or perhaps in the field and coming back to you via telemetry. And at that point, with all your tools and techniques turned off, you're on a production kernel, it will be very hard to diagnose the fault. Prove locking allows a different way to surface the problem. And it basically is based on the idea that these two fragments can be run by a single thread. You can have lock subsystem, lock driver, and at that point, prove locking or lockdep will remember that sequence of locks. It will remember that the subsystem lock was taken first and the driver lock was taken second. It will then, you can eventually run the code that we've shown here in thread 2 in the same thread where it takes it in a different order. And it remembers that lock sequence as well. And at that point, we can already say there is a bug in the locking order. Because if you have a system where you take the subsystem lock first and the driver lock second, you should never, ever, ever take the driver lock first and the subsystem lock second. So it doesn't matter whether it's in one thread or whether these are happening in different threads and whether they happen concurrently or not concurrently. The key thing is this can surface the locking problem without having to expose us to the deadlock, simply because we can observe that things have happened in different orders. So this is very, very powerful. It can also be used to look at certain types of lock nesting. So there is a relatively poorly understood distinction between spin locks and raw spin locks. And the distinction is all about how the preempt RT kernel is implemented. There is an extension to prove locking to check for correct lock nesting. And that will help you bring out problems that can only manifest on preempt RT kernels, again, as deadlocks. So prove locking doesn't just help us get this right, it also is a fundamental part of making your code more robust and ready for preempt RT, which is coming. So as vendors, turning on that additional prove locking feature to verify lock nesting is a very wise thing to do to help you get ready for preempt RT to come in the next few months. Other super powerful option is the kernel hardware assisted address sanitizer. This one's particularly important to an ARM audience because I believe that it's more or less unique to ARM because it's based on a ARM MMU feature. And that's a special ARM feature called top byte ignore. This was designed to create things called tagged pointers. So basically they take the 64-bit address and they say only the bottom 56 bits will be used to figure out what bit of memory we're going to talk to. The top 8-bit is a tag, and the tag can be used for multiple purposes. It can be used for debugging, as in this case. I think it is also used in Apple phones as a way to optimize heap allocations. So it's an interesting feature. It can be used for a couple of different things, but in the kernel, it's used for this debugging technique. And it's very similar to the address space sanitizer, but we can, instead of having a bitmap saying which bytes are valid, we have a, oh, I can't think how the chunks are. I think it takes a 64-bit window and tells you what the tag is supposed to be on that 64-bit window. And in other words, what happens is we have a shadow of memory telling you what the tag is supposed to be for every single piece of memory. And if you take a pointer and overrun it, you can imagine the top byte doesn't change. So then you end up accessing a memory address where you are accessing it with essentially the wrong key. The tag in your pointer does not match the tag held in the shadow data structure, and we can detect that that's an illegal memory access. And the reason this is a really powerful technique, so compared to the address-based sanitizer, which is the bitmap, and we compare the bitmap of valid, not valid, we can now read a pointer and say, is it pointing to its original chunk of memory or not? That's more powerful because we can't overrun and accidentally hit valid memory that we weren't supposed to read. It's also fantastically good for finding use after free, because when you free memory, you set it to a reserved tag that is never handed to true allocated memory. So whenever you hit a use after free, it will always have a bad tag, because when it gets reallocated the next time round, it will have a different tag. And if you use the old tag, even when the memory's been reallocated, you can't read it safely. This has all the same performance problems as kernel address-based sanitizer. It's an instrumented memory access that is going to have to check a data structure. So it will make your kernel slower. But it is able to find these it's tremendously robust at finding memory access problems. So, oh yes, this is I'm not going to speak about this one into detail, but there is also a mechanism where the newest features in the ARM v8.5 and v9 hardware add additional layers above it, so we can go even deeper. But I forget the precise details of exactly what we gain and lose compared to the standard top byte ignore. So again, it's an MMU feature that allows you to split that tag even further and more specific, so that the, oh yes, sorry, I'm with it again now. Sorry, yes. This is basically allowing us to use particular instructions to access memory, so that we can claw back some of the performance that we lost in managing these tags. So in other words, it allows you to do the same type of analysis that we do with this tool, but we get to use hardware opcodes that will check the tag and blow up if things go wrong. Finally, I want to talk about kernel kfence, which is perhaps interesting because it is designed to be turned on in production, unlike most of the others we've looked at. So it's kernel electric fence. The name is a homage to a user space memory debugger from the 80s. And it's like other MMU technologies. It's going to try and use the MMU to detect use after free and valid free out of bounds accesses by placing guard pages after valid allocations. So it's powerful, and when you apply it to all of memory allocations, think valgrind or kernel address-based sanitizer, it has a massive overhead that we can't afford to pay. What you have in kfence is a low overhead alternative, which is just to instrument some of the memory allocations. So when you allocate memory, it's a bit probabilistic. Some of them will be allocated with guard page after them, and some of them won't. And it's based on a timer. And when the timer expires, and we've not got too many allocations at once, then we will allocate with the guard page. The principle behind this is we're trading performance for precision. So most of the allocations that we have overruns on will not get instrumented. But if you have a fleet of similar machines, if you have lots and lots of similar devices, either server farm or your collection of Chromebooks, whatever else it is, and you deploy K-Fence to a wide number of devices, and you have appropriate telemetry, then the telemetry will come back to you, and eventually you'll be able to find bugs that you might not have found in your lab. It does rely on telemetry to come back, because this means we are effectively provoking devices to crash in the field in order to chase these things down. It usually implies that you have a certain security posture where you would like the devices to fail so that you can fix security bugs and things like that. I believe somebody asked about hardware address-based sanitizer. 2 questions. Does it work with LLVM and GCC? I believe it works with both. So the sanitizers grew up in LLVM, but the hooks that they used were adopted by GCC as well. And in terms of performance, the performance is not that much different to regular address-based sanitizer. So my rule of thumb is about 3x. It's going to be what's the word? It's going to be workload dependent, because it will depend how long you spend in the kernel. It makes the kernel 3 times slower. It doesn't make the system 3 times slower. So if you spend all your time doing complex ray tracing calculations in user space, you won't ever see the difference in performance. If you spend a lot of time going through doing I/O and networking, you'll see a significant hit to your performance. So it makes the kernel about 3 times slower on average, but even there, it will depend on how often the kernel is accessing memory. That gets us through to the end of what I wanted to say about failing early. So we're now going to move on to what we call the stories, which are, stories is a slightly idiosyncratic name, but we didn't want to say use cases, because use cases are typically specific and are used to guide software architecture. Whereas I want to tell stories that are deliberately slightly vague, so that I can bring in multiple debug tools to address them by interpreting the vagaries in different ways. So that's why we call them stories, not use cases, but they're serving a similar role. They're a synthetic distillation of common problems that we might have. So the first story that we present to you is called I Can't Reproduce, but My Customer Can. And we have the tagline, everything was great when I ran on my desk, we've shipped it, I've delivered to my customer, and they keep reporting this odd behavior. It's going to be really hard for me to reproduce, perhaps I don't have the equipment, or I don't have all of the software. And then finally, I've already been on 3 on-site visits this year and I don't want to travel anymore. I'd rather try and solve this remotely. This is particularly applicable during COVID times, because the probability of being sent on site has gone down significantly. So the scope, odd behavior is deliberately left undefined. So exactly what behavior the customer is seeing, we aren't going to define. It is quite possible that the level of skill the customer has may differ from your own. And that doesn't even mean that, I'm not talking about just general level of software smarts. You know, if they're a specialist in writing a particular part of the system and you wrote the driver stack, I would hope that you know more about the driver stack than your customer does. That's what should happen. That's the way it should be. It doesn't mean that they are unsophisticated necessarily, but the understanding that they have of exactly how your system works, potentially the internals of the Linux kernel, may not be equivalent to your own. I'm assuming that the customer is external. If you're working with, it can happen with internal customers, but if you are on overlapping time zones, there is a lot you can do with telepresence technologies, like conferencing tools, screen sharing, VNC, pair programming tools, things like that. You can actually, get on a headset, permanent voice call, see each other's screens, and work together. Particularly if you use things like VNC that allow you both to type. You could say, "Oh, can I try doing this bit for this section?" It is much less common to be allowed to type into customer keyboards remotely, because video conferencing tools don't allow the sharing of keyboards. They do allow the visibility of the screen. But yes, I'm going to assume the customer is external, or at least you're not going to use VNC as a tool to try and sit with them. The consequences of this are intrinsically that debug cycles will take longer than usual. If you're being given some evidence, you think about the evidence, you propose some experiments, and then the customer runs them and you get back, that is going to be a longer debug cycle than you firing it up, feeding it, looking at, changing it, feeling it, and so on. That level of skill may mean that your customer is not very experienced deploying certain Linux debug tools. So it does imply that the deployment of debug tools has to be something you can describe and document for your customer. And finally, we're likely to be leaning towards tools that allow us to exfiltrate data back from the customer to our desk so that we can analyze them. Obscurely, during this use case, the most significant tool that I think really has to be used and sometimes gets underused is source navigation, static analysis essentially, but helped by yourself. Source navigation is always a useful tool. It's always a useful tool. But for remote diagnosis, the importance increases because of those long debug cycles. Long debug cycles imply that if you can look at the evidence in the printk buffer and spot particularly the absence of error paths, if you've been using the source navigator and you've said, right, so one of three things has happened, and then you use the source navigator to traverse each of the three options, and in one of them you find a printk, then you can go back to your printk log and prove that that branch was not taken without any additional tracing. So it's definitely combined with printk logs that the source navigation becomes a remote debug tool. And yes, it's that you basically look at the printks and you have theories about the multiple ways it could go wrong. And you might be able to prune some of them by source navigating a few layers deep in each of the branches and figuring out that, oh, well, that printk didn't happen. That's what I mean by saying this is a remote debug tool. I mean, like I say, source nav is always a valuable thing to have. In terms of how to do it, I don't care how you do it. There are lots and lots of indexing tools. This I've opted as a kind of same default. Is if you type make cscope into the kernel build system, it will list the files just for your architecture, so that you're only looking at files that match your architecture, and it will then run it through cscope as an indexer. There are other things you can do, make ctags, and it will use the ctags version of source nav. It can also do GNU Global. They're all integrated as there, but effectively one of those three options will generate you a symbol database. And then you can rely on editor integration or perhaps cbrowser to study the cscope database. I like cscope because it had a certain power that some of the simple tags didn't have, although I think the exuberant tags do. And then finally, there is one annoying gap in some of these tools, and some of them are confused by the Linux kernel's use of structs. The Linux kernel doesn't usually type def structures. And that gets you to a difference in parsing called the difference between a declaration and a definition. When you have a prototype and it says struct foo star this, and you haven't included the header file, that's allowed because the size of a pointer is well known, regardless of what's in struct foo. What that means is if you ask to go to the declarations of struct foo, there are lots of them because they appear in every single header file. And you get, sometimes for commonly used structures, you get pages and pages and pages of declarations, when what you actually want is the definition. So if you have a tool that doesn't allow you to find the definition easily, augment it with a git grep. And there we're just relying on the source code formatting rules in the Linux kernel, which says that in the definition, you'll always have a trailing open curly brace, whereas in the declarations, you'd almost always see that followed by a star for the pointer of an argument. The other aspect of effective source navigation is to be able to map printk messages back to source. When you see a printk message in the log that you've got back from your customer, and you're not 100% sure what it does or where the code comes from, you need to be able to map it back to find the actual source where it is, find out what the arguments are, find out other printks nearby, so that you can reason about which paths have been taken through the code. So in this case, we've got a message, it's got a time tag, it's got a a tag of some other sort, I'm just XYZ in this case. It's usually the driver name or the device name. And we've said that we found 10 widgets. When we want to convert that into regular expression, obviously we don't include the timestamp. We also do not include this tag. Two reasons for that are that a lot of the time that tag is dynamic. It has come from the device name, in which case it won't appear in the sources anywhere, because it's a fixed string and a number, and the combination will never appear anywhere. The other one is that it's quite often, even if it is not dynamic, it is quite often the driver name. And the macros add it for you. When you do things like PR info and so on, the macros add that tag, so it still won't appear in the source. So once we've stripped off all the sources, we're now looking for things that look like variables within the string. And we end up with found wildcard widgets, and that's what we search for. If we were really paranoid, we might drop the S as well. It's not a common habit in the Linux kernel, but some programs split out plurals from non-plurals. So yes, once you have got your messages, you want to try and turn them into a regular expression of the wildcards and then look up in the source code. I'm going to stop lecturing about source navigation now. We'll look at real tools. Okay, so PrintK is, again, fundamental to remote diagnostics. In fact, I could not explain the value of source navigation without saying that you've already got the PrintK and dmessage buffers. So yeah, it's a robust and almost always on trace system. It's absolutely critical for remote diagnostics. You should always deeply study existing log buffers provided from customers and use those to form theories about the possible failures. An obvious approach to trying to cope with these I can't reproduce situations is to study the log buffer, work out what it is that you can't make decisions on because there's not enough evidence, and then enrich all the different branches that you've got worries about with log messages to prove and disprove each theory that you have about the possible failure. And that's the combination of PrintK, going to the source nav, generating theories, adding log messages, and then cycling again. One thing to be aware about PrintK, which is being worked on at the moment, newer kernels will not have this property. They will still have costs associated with the PrintK, but the performance is going to get better very soon. But for now, I'm going to describe, this was definitely true in 5.14. I know there was work for it in 5.15, but I don't know if it's complete. So the reason performance sucks on embedded systems based on a UART console is that the CPU spins waiting for the UART to complete. This is the technique the kernel is doing to avoid interleaving problems with the printing system. And if I point out that half a line of text at 115200 baud takes about 3 milliseconds to reach the output. So it's not that the performance of the printing going to the screen is causing you the pain. What's causing you the pain is that CPU is not doing anything else. The load on CPUs that print to the UART from within the kernel is enormous. And that means that heavy logging to the console will cause Heisenbugs, almost for sure. There are mitigations. The simplest mitigation is not to send it to the UART. So if you disable the console, you put quiet on the kernel bound line, and then extract the dmessage buffer by some other means after the fact, then we can have lots and lots of printing, because it's not the formatting of the string that's expensive, it's the sending it to the UART. So turning it off will help. So what is, if you're curious, incidentally, user space use of the UART does not have this property. User space use of the UART puts the characters that you want to print into a backlog, and then interrupt handlers wake up every time the FIFO runs dry, copy another 8 characters from that buffer into it, and then you go back. So nothing is busy waiting, it's all interrupt driven. And the work that is happening in the kernel community at the moment is to split concepts of prints to UARTs, so that most of the time on a not yet failed system, the logs can go and be conveyed out by interrupt. And then when a system fails, you have to do the classic wait for the UART techniques. So it's trying to work out how to distinguish which you're in at any particular mode. So that's what's being worked on to try and improve this situation. But for anybody who's working on older kernels, then this is, yeah, it will cost. As you add those log messages, the the performance of emitting those log messages to the UART goes down. Simplest way to avoid it is to use the demessage buffer instead. The other thing that I think is really wise at this point is to make sure you understand how PR debug and dev debug work. I'll put it in explicitly. So dev debug is a macro that prints a debug message with the tagged with the driver name, and PR debug is printing a debug message potentially tagged with, sorry, the device name. Dev debug will tag with the device name. PR debug will either not tag or tag with the driver name. Either way, both of those macros on a standard production kernel that does not have dynamic debug enabled are disabled to the point that they are compiled out. So when they appear in your source code, they're not just going out at level 8. Level 8 is PR debug? No, it's some sort of macro. So because the kern debug, underneath the covers, these called print K. The first bytes of a print K string are the log level, and that's things like kern warn, kern panic, kern emergency, kern debug. Kern debug is level 8, and the default console log level is typically level 7. So this is good from the point of view of the highs and bugs above. If you print anything at kern debug, it will only go in the demessage buffer. It will not go to the UART. But more than that, if you're using the accessor macros, dev debug and PR debug, those are not in the kernel by default. They're simply compiled out. There are a couple of ways to avoid that. You can hash define debug in compilation units that you want to have debugging from. So one thing that you might be doing if your customer does not give you enough information first time round is to work out where to sprinkle the hash defined debugs into which drivers to activate additional debugging. The other option is to use dynamic debug. So dynamic debug essentially allows you to turn off and on or off these debug messages. It allows you to stuff the kernel full of very, very rich log messages, and then for different debug cycles, you can run multiple experiments by changing the kernel command line to activate and deactivate particular log messages. It's an alternative way to chase down the Heisenberg problems. You can use dynamic debug and then log to the UART because you can control the volume of trace messages. Other things we could use to try and gather information about the system. So DebugFS. DebugFS is simply a virtual file system that allows certain state from the kernel to be presented to user space. And different subsystems have got different config options to enable it or disable, but it's basically a file system that contains information exported by drivers that is pertinent to debug. Again, you could quite easily write tools that the customer can run to scan DebugFS and gather state and allow you to study it later. In particular, any driver that uses the regmap accessors. So regmap is a mechanism to somewhat abstract register accesses so that drivers can, it allows you to abstract things like different memory mapped drivers with slightly different layouts of their registers. It allows you to abstract the difference between I2C and SPI when accessing a low-speed peripheral. But if you have drivers that use regmap, that does give you some very significant and useful debug techniques, which is that you can simply capture the register state from the device and provide it back to you. You can tell your customer to give it back to you. You can even, if you get grep for this particular option called regmap allow write DebugFS, you can do experimental pokes to the registers from user space to try and unwedge or unstick a peripheral that's not doing what you want. You can do things like poke to its reset register to see if it gets better and things like that. So the main config is DebugFS, and that will bring it on. This is not a config option. This is considered to be so dangerous that it's something an individual developer greps for and turns on if they want to play with it. But the code is there in the kernel if you do want to do so. So we're going to bring out some bigger guns now. We've tried those simple tracing tools like printk. We haven't quite got what we wanted. So we're going to attempt to do function tracing. So I can only show you the fundamental idea behind function tracing, which is that from the compiler's point of view, we add this profiling option PG. And what that does is at the entry to every function, it's called the function preamble. So there's some housekeeping. When you make a function call, the compiler generates some housekeeping before it starts generating the opcodes that your C code represents. That's called the preamble. So within the preamble, it makes an additional function call to a function, as it happens, called _mcount. During, I believe, the linking process, the kernel modifies the code to literally replace the call to mcount with a no-op, but creates a data structure that tells the kernel where to find it. So in other words, when you boot a kernel that has function tracing enabled, inside every function point, inside every preamble is this spare no-op, which is almost undetectable from a performance point of view. It clearly will affect the iCache utilization, but for tight looped benchmarks, it's still almost impossible to detect that no-op. It will have a cost, let's be clear, it does have a cost, and it's mostly measured in iCache utilization, but it is actually quite hard to find in benchmarks. But what the kernel can now do is it can choose whether to replace that no-op with a call to its own tracing infrastructure, which basically is now a branch linked to ftrace caller. That means the kernel can selectively intercept the entry of every single function in the system that is not in line, and log when it's happened. So some quick ideas about how to do it. So like I say, ftrace has almost no cost when it's disabled because those no-ops are very difficult to discover. Once you have got it enabled in your kconfig language, you can configure it from debugfs. It doesn't require any specific tools at all. You can cd into the tracing directory, you can echo function to the current tracer, and you can turn tracing on. And what that would do now is, because we have not provided it with a block list, every single function in the kernel will have had that no-op replaced with a call to the tracing infrastructure, and it will be tracing every function call. And you can perhaps imagine how powerful that can be in tracing what has happened and which paths have been taken. And again, your customer can just then turn this on, wait for the problem to reproduce, and copy the trace log back to you for you to analyze. You can also configure ftrace in the kernel command line. So there's a couple of trivial examples here. The first one is to turn on ftrace function, which again is tracking each function entry point. And we've turned on a filter. So this is an allow list that says the only things I want to filter are starting in my drive underscore. So this is assuming you're working with a driver that has prefixed everything with my drive, including some of the internal helper functions. And we only want to study how that driver is interacting with itself. You can obviously extend the wildcards to include the subsystem it belongs to, so that when the driver makes subsystem calls, you can see that, because that will literally it's only calls that match that pattern that would create any message in the trace log. So it's a true allow list. The alternative is a block list. So the block list allows us to look for certain functions that are usually dull. And all of the RCU lock, spin lock family are a little bit dull because they're so noisy. There are so many calls to these things that they fill the trace and make it almost impossible to navigate. The other subtle thing that's happened here is I've asked for what's called a function graph trace, which basically on function entry point, you can do things to mess with the call stack return graph and arrange for you to also be called when the function exits. So by using function graph, we do some additional trickery on the stack that allows us to track both all function entry and all function exit, which does give you a really strong visibility of where you are in the system at any given point. So both of the traces can be based on whitelist or allow list or block list tracing. Somebody's commented there are many other ways to use ftrace. Yes, there are many other ways to use ftrace. As I have mentioned, we can only cover the essence of each tool. So yes, I'm not going to go through Perfetto. I'm not going to talk about trace command in this, but we do have training on those topics, but they're not in scope for today's talk. So we can extract trace information in lots of different ways. It's accessible to user space. You can arrange for parts of the trace to be passed to print bucket. That will have huge performance costs, and it can only work with trace points. You can't take the function tracing, but you can do trace points and output them. You can arrange them to automatically dump on OOPS. So you can arrange them so if something's internally gone wrong, it can dump them out. And you can use things like KDB. So KDB actually KDB is the on-target version of KGDB, if you like. So KGDB allows you to connect external KGB to it. KDB puts up a prompt on your serial port that allows you to type commands. And one of the commands that KDB offers you is a way to look through the ftrace. A particular nice thing about KDB in that instance is it gives you a pager and a GRET mechanism. So that if you are working on a device where you don't have a scrollback mechanism, i.e. the screen as opposed to a UART, KDB can actually be quite helpful. There's lots and lots and lots of tools that sit over the top of it. I think it's fair to say there should be trace command in here, but trace command is actually in the same source source control system as Kernel Shark. So when you go to get Kernel Shark, you'd also find trace command. So yes, there's lots of different tools you can layer on top of ftrace to help you wrangle the information. Kernel Shark is a particularly common one. That helps you navigate the traces and find the information you're looking for in the density of stuff. There's a question about looking up the C code. We've got that coming later. So that will be answered in the fullness of time. Final thing so I'm hoping to get to a break shortly, but I'm going to finish this particular story first. One option that comes up, this is much more for server people. It can work in embedded situations, but it is perhaps more for server people, is rather than working with this anemic trace log or trace information, we might just like to get a memory image of the whole kernel. And if we've got a memory image of the whole kernel, we can run proper external agent debuggers on that memory image and look at the memory, look at data structures, find out what's going on inside. So there's a couple of techniques to do this. The inbuilt self-hosted one is called KDump. So KDump is piggybacked on the top of a technology called KExec. KExec allows you to switch from one kernel to another kernel. It allows you to use Linux as a bootloader for other Linuxes. So what can happen with KDump is at the point something fails, so at the moment the main kernel panics, it is able, during its panic handlers, to KExec and launch into an entirely new and different kernel that hopefully is using sufficiently little hardware that it's still able to survive. So there's an example of this at the bottom. We're launching that additional capture kernel. And within the capture kernel, there'll be a file in /proc called vmcore, which is the memory image of the old kernel. So with that, we can extract the entire of the memory image for the last kernel and exfiltrate it however we like. We could write it to disk, we could set it over the network, whatever drivers we have in the new kernel, we can use that to exfiltrate the image back to our workstation, and from our workstation we can then try and study the crash. To do this, you do have to allocate space during boot up to hold the crash kernel, both the crash kernel's text section and any memory structures that it needs, so that it doesn't overwrite the main kernel's memory structure. So to have this, you have to silo off a fairly big chunk of memory, which you probably wouldn't choose to do on production embedded systems, and you might not be able to do on non-production debug embedded systems because there's not space. Once you have the memory out, there are tools that you can use to analyze it. You can try and trick GDB into loading them, but most people use this thing called the crash tool, which is, it's actually a GDB, a more complex GDB front end that includes powerful analysis tools like Linux Aware analysis tools like thread awareness, extract the ftrace buffer, and other things. If you are one of these poor embedded developers who don't have access to things like that, you can also use other bespoke tools to try and capture core images. What I'm describing here is core image debugging. And you can use kdump to get core dumps. You can use things like JTAG debuggers to attach to a failed system and extract out the memory image of the kernel. You can use bootloader trickery to try and recover the RAM contents. If you dump the caches in your panic handler and reboot into a bootloader that then allows you to extract the memory from the network, that again is an acceptable way to get a core dump. I can't talk about those in any detail beyond the fact they're possible, because they are device dependent, debug tool dependent, dependent on the memory technology, depending on whether your bootloader can reprogram the RAM refreshes fast enough and so on. They are things that you can implement, and then you can provide just enough glue to allow the crash tool to load them. But other than saying that they are possible, we can't give you references because it is very much machine dependent. It's the sort of thing vendors provide. And finally, I am just going to show you a couple of, when you get into kdumps and crashes and oops traces and everything else, anything that's going to show you registers and addresses, it is useful to have some idea of the memory map of the machine. Simply so that you can look at a pointer or look at a value in a register and say, that doesn't feel right, something strange is happening here. So you should always have some idea of what, say, a kernel pointer should look like. In the case of 64-bit systems, that's quite easy, because it does vary depending on the size of the page and the number of levels in the page table. There are text documents in the kernel documentation to summarize all this for you. But kernel pointers ultimately start with Fs. All kernel pointers start with Fs. So if you see the kernel having dereferenced a address and it doesn't start with Fs, if it's not in something like copy to user, then you know that you've got a bad pointer just like that. You can also look at types of pointers. So you can distinguish between the main kernel image. So these are the big pages that I mentioned before, against the virtual memory pages that come out in other places. You can spot, I beg your pardon, I've been pointing in the wrong place. So the direct map kernel memory is down here, and you can spot the difference. So the vmalloc, this is part of the kernel address space layout randomization. The text section isn't part of the directly mapped kernel, so that we can move it around through memory. It ends up in the virtual memory address space. Like I say, the main one is distinguishing between the direct mapped kernel memory and the virtual forms, because knowing the difference between the two again helps you interpret stack dumps if you know that you're expecting to see virtual addresses or you're expecting to see direct mapped addresses. Yeah. Kmalloc should be giving you pointers out here. Vmalloc should be giving you pointers out here, for example. So yeah, you should always have some idea of what a kernel pointer should and shouldn't look like. You should be able to recognize then that this pointer is a data. You quite often can't tell the difference between pointers to data and pointers to text, because they do have very similar patterns. It's just they appear one after the other. Although you can look at your kernel image and find the difference. You can say that, yeah, that looks like a pointer to text. That's a bit weird. I wasn't expecting that, and you can double check that. It's something worth knowing when you have oops traces and you're still in the machine world a little bit. The other thing it can be useful to have an idea about is the stack. This is more for the 32-bit ARM people, to be honest. So you have the stack, and it's a chunk of memory. In the case of ARM page sized, I believe. You have a register pointing to it. What's interesting is the task structure. So the task structure on ARM 64-bit systems has the thread info included in the task structure. And it then uses some additional registers to find it when you need to use it and access it quickly. And then that switches out when you switch it to user space. ARM doesn't have the combination of the supervisor mode stack pointer and the user mode stack pointer. It has just one. So it uses arithmetic to find the thread info. and it finds the thread info at the bottom of the stack, as at the most extreme end of the stack, and stacks grow downwards. So the first thing that happens on a 32-bit ARM system when you explode your stack is you tend to lose the ability to find the task structure. So again, these are just little bits of information about memory layout that can be useful to reason. If you find that the kernel is really struggling to figure out what it's executing, it might well be that it's down here and it's looked up the wrong thread info. Because as soon as you're out of this space, if you ask what my thread info is, it'll give you the wrong value. If you've overflowed the stack and then ask what the thread, ask to know your own thread information, it can't tell you. It will go and look up completely the wrong data structure. So certain properties of stack overflow crashes on ARM are especially hard to read. Once you know that, it doesn't help you that much, except that when you see something that looks really freaky, it's one of the options that you bring up to your mind. So at that point, I suggest we have a short break. This is a very, very dense presentation. Things do go a little bit faster after this point. So we've got 4 stories left to go. And I will start talking again at 1/2 the hour. So you've got 5 minutes just to shake things up, move about, whatever else you want to do. I'm going to double check the questions. I'm quite happy to keep kind of talking, reacting to people, interacting. But I'm not going to go back to the slide material until 1/2 the hour. Or on the hour if you're in India. Does top byte ignore and memory tagging affect the normal addresses? So that's a good question. They do, yes. But you should still see a bank of Fs in them. So yes, the canonical tag for the kernel is 255. If you think about the top byte as being a tag, the canonical tag is user space is 0s and kernel space is all Fs. When you have top byte ignore on, I believe the canonical tag might actually switch to 0, but you will still see a bank of Fs in the top 16 bits, I think. Again, these do move slightly depending on the depth of page table, which is why I'm being a bit vague. This is the normal case. 4K pages, 4 levels is mostly the normal case because it provides you very good ARM32 compatibility. If you are working on things like Red Hat Enterprise Linux, they are adopting 64K pages pervasively for ARM64 systems because it's a performance benefit. It's very interesting, actually. 4K pages, if you think about this. So the first ARM system to have a modern MMU in it was, I believe, developed for the Apple Newton, which was a PDA that tanked because the technology wasn't quite ready. It was a full handwriting recognition-based tablet computer, and it filled the niche that was eventually occupied by the Palm Pilot, which decided it wasn't going to do full handwriting recognition to cope with the technology of the day. Anyways, that was the first device to have 4K pages in the ARM world. That device had 4 megabytes of memory in it. And here we are in the era where, you know, the machine by my desk has 32 gigabytes of memory, and I'm still running 4K pages. So 64K pages do offer some interesting performance benefits because you don't spend as long walking the page table trying to find data structures. So they will change and when you go to 64K pages, you will see slight changes to the positioning of these addresses. But ultimately, there are still ways you can tell the difference between the two, yes. So I decided about page sizes is partly because there's not any other questions, but Okay, so welcome back. I hope you enjoyed your break. We're now going to move on to a story called My Widget Missed Its Deadline. So you can read the story. Essentially, we've got a widget that's critically important we handle fast enough. We're assuming some kind of real-time thing. When the system gets busy, code starts to miss its deadlines. You can see I've called it we end up dropping frames, which very much a testament to my set-top box background. It doesn't have to be frames. And my QA team are beating me up because we promised them a nice smooth user interface. So what we've left vague, is missed deadline. We haven't said if it's an interrupt handler, a tasklet, real-time thread, regular task. It could be any of those things depending on the nature of the system. When the system gets busy, could be system testing. We could be doing synthetic workloads to try and deliberately break things. The fact that it's the Q&A team beating us up probably means it's a system test, to be honest. We also assume here that the kernel remains functional throughout. So in the previous test, for example, I hoped you could retrieve the ftrace buffers after the fact, but I did show you how to extract them from unusual circumstances. I said you could extract them in unusual circumstances. I didn't show you how because we don't have time, but we mentioned there are ways to extract in-memory buffers without having to have the system fully functional. In this case, we are assuming the kernel remains functional throughout. We've just missed a deadline, but we're not expecting a crash. We're going to assume that for things like failing early, we can add code to the widget driver to detect when the deadline is missed. This is very, very common. Essentially, when you are running the code to do something, it's quite easy to add something in that code to find out if it's run quickly enough. So we should be able to have some kind of message at the point of failure to help us navigate the trace information. Finally, we've assumed that apart from a message at the point of failure, that print K is not going to be very helpful for this type of problem because it is too difficult to decide where you want to add extra log messages. Print K only tells you what you asked to know. And since we don't know what it's doing while we're missing our deadline, that's our debug goal, is why has it missed its deadline? What was it doing when it should have been meeting its deadline? So print K is not of great deal of use there because you can't figure out where to sprinkle it. So first up, back to our friend ftrace. Clearly, ftrace has a role in its original form of tracing. We could start an ftrace, and that might show us what we were doing when we missed the deadline. We've already covered that use of ftrace. However, there are some alternative traces that might be interesting to us. So first off, even very lightly loaded systems can miss deadlines based on interrupts if there are long periods of interrupt lock or bad task priorities and things like that. So ftrace can be used not just to show the functions that are being used before we miss the deadline. They can also be used to look at other things that are happening shortly before missing a deadline. Like I say, function tracing would be great for this. It's also moderately intrusive. So we might want to find out lower intrusion ways to try and get interesting information out. So some other traces that can be interesting. ftrace allows us to do things like track how long IRQs are disabled for, track how long preempt is disabled for. Preempt disabling means that you can't run the highest priority task in the system because you've prevented preemption. So you can use any of these tools to look for long periods of lock. If you have got things that have to cope with an interrupt firing every 16 milliseconds and IRQ's off says that you turn off interrupts for 20 milliseconds, you need to fix it. So ftrace will tell you where it is and it will give you a stack trace of the point where the IRQ is disabled. Wake up and wake up RT is essentially going to give you a similar sort of things that you can do for tasks instead of for interrupts. So if you've got real-time tasks that are made runnable but don't execute because something else is happening, then wake up RT is a very useful technique to find out why we've got this long gap between being made runnable and executing. And at this point, I'd also like to introduce trace points. So static trace points are best understood as advice from kernel developers about what is interesting within their subsystem. And one of the most powerful set of trace points in the system is the scheduler trace points, which are basically advice from the Linux scheduler authors about what interesting things are happening inside the scheduler. And if you add this to your set of tracing things, this is how you can turn on all the scheduler events in ftrace. then every time the scheduler makes an interesting decision, it will copy it into the same trace log that ftrace gets traced into, without having to turn on ftrace. Right, so we can set the current tracer to ftrace, which is what we did a little while back. You can also leave the current tracer alone, leave it as no op, and instead observe what's happening with static trace points. These can also be hooked up to lots of visualization tools like Perfetto and things like that, which can show you the thread schedule of each core. It can tell you what each core is executing at any given time. So if you've got a point where you've missed a deadline, you can look back over what tasks are happening on the system or what interrupts are happening and get a sense of how you have missed it. And then you can do a much more targeted trace on whichever task it is that's causing you trouble, rather than doing pervasive watch the whole system and figure out what's going on. So we can use tracing to try and figure out what decisions were made, particularly about scheduling, before we made a scheduling mistake. Now, this story is a little bit vague, and one of the vagaries is we don't know why we missed a deadline. One possibility, which was expanded in the previous one, the ftrace one, is we were doing something else when we should have been servicing our deadline. And if we were doing something else when we should have been servicing our deadline, then that's the way we look and find out what we were doing instead. The other possibility, of course, is we simply don't have the CPU horsepower to achieve what we're trying to achieve. So in other words, if you find out that what you were doing when you missed your deadline was try to handle the previous deadline, then we want to start looking at something like a profiling tool. We want to try and find where time is being spent and look for opportunities to make our system more efficient. As ever with profiling, there is a lot of philosophy behind it. You should always make sure you have sane algorithms before you profile. Although profiling can surface inefficient algorithms you didn't know were there and give you the opportunity to replace them with efficient algorithms. So Perf is a good system-wide profiling tool for Linux. System-wide means we don't care which process is running. We are just setting a system-wide periodic interrupt. Most profiling is based on a periodic interrupt, and every time it interrupts, we look at what task is running and what the stack trace is and which functions are involved in it. And by running that for a long period of time, running a representative workload, we'll eventually hit most of the interesting points in the system with our periodic timer, and we get a nice view of where, it's an approximation, but we get a good sense of where most of the time in the system has been spent. If you're curious, the diagram on the right is the simplest version of this. It's a thing called perf top, which basically goes across the entire system looking for which functions were hottest. And you can see on this particular system, which was my Intel laptop, the hottest thing was the pulse audio read functions. Not quite sure it was read, because all we're doing is playing music. So this particular system was just playing some music in the background, and we're not seeing the idle function. In this particular configuration, we don't see idle activity. So the most expensive thing it was doing was playing music, but that's mostly because it wasn't doing anything else at the time. Like I say, perf is a hugely complicated and powerful tool. I could talk, I have a talk for another 2 hours that would tell you about perf in detail. For now, I could just give you some entry points and names to look up if you want to do some further reading. If you want to get really specific into particular parts of profiling, one of the things that can crop up is you realize that you're on an SMP system, and the reason your performance is going away is because the locking costs. So if you are concerned that what you are suffering from is some kind of lock thrashing or other related thing, there is a specific lock profiler that you can set up in the kernel, which will look for heavy contended locks and things like cross CPU data sharing that are costing us things. It's a very, very special case. Like I said, I don't think I've ever actually used this for any of the problems that have presented me over the last 15 years, but several people have, and it is particular to particular structures where you've got particular types of sharing and what you're trying to optimize. So it's an interesting tool. It's a very exotic tool, that particular one. Moving on to the very much more general purpose hammers. So ARM, we're on an ARM system. There are other things we could be doing to try and understand what's going on. In particular, if you're an embedded system and you want to have some kind of trace-based analysis, but you conclude that ftrace is too expensive, we can start reaching out to hardware-assisted trace like CoreSight. So CoreSight is a generic name for most of ARM's debug technologies on a chip, but one particular one that comes up for tracing is every processor on the system tends to have this thing called the ETM, the embedded trace macro cell, I believe, which basically throws trace information into a funnel, hardware funnel. So all the cores on the system are busy providing trace information into this funnel. There's even actually a thing called the STM, which is a software controlled trace module, which allows us to put in software oriented trace information like context switches or things like that, so that you can interpret the trace information coming back from the core itself. The result of all that, it goes out into a trace capture buffer. If you have, CoreSight is also the domain of the SOC vendor. Although I think the embedded trace macro cell is part of the hard macro cells for the core, so that if you've taken hard macro cells from ARM, you've got one of those. What happens with the funnel and the downstream stuff is configurable by the implementer. And again, if you own your own cores, you're doing your own hardware design. Even ETM doesn't have to be there, although in practice it usually is. That trace information can go off chip. It can be sent out to a fast serial device and captured by an expensive piece of hardware like a Lantern Bank. It can also be stored in memory. And if you remember, the system is still running in this case. So we could configure CoreSight and arrange for it to be tracing into the software buffers and then extract that with the perf tool. There are several videos about this little various Linaro Connect things. My summary of how to use it is extremely Spartan here. There's a library to parse the trace data, and it's integrated into perf. So you can configure perf to set up specific CoreSight experiments. Finally, finally, for the widget missed its deadline opportunities, you could also deploy eBPF. So eBPF makes a lot of sense in the server domain. It makes some sense in the embedded design domain, but I'll explain why it's perhaps less significant in the embedded space. So eBPF, let's start without eBPF. We have some source of interesting events within the kernel. They go out into in-memory buffers, they then perhaps go out, in this case, via trace command to be stored in user space, or perhaps go into user space for event processing if you're doing profiling. That is a relatively heavyweight flow because we've got this big stream of information coming from the kernel out into user space and being digested in user space. What BPF gives you the opportunity to do is to write programs in a variety of languages, but primarily C, that can attach to specific hook points in the kernel and make decisions in the kernel using this kernel-based virtual machine. So if you want to gather certain statistics, you can digest the statistics in the kernel. And so we've got our event stream, and we're very, very quickly at the earliest opportunity reducing that down to the information we're trying to extract. So it allows us to write essentially custom profilers and custom debug techniques. The reason it is a harder sell in the embedded space is because you can already write C-based analyzers and inject them into the kernel, and then you recompile the kernel and you run it and you're good. So for the embedded space, eBPF essentially competes with a edit, debug, run kind of cycle. The reason it does have some benefits is that it is subject to very aggressive verification. So one of the phenomena with writing debug tools is if you get them wrong, you might crash the kernel because you've messed up your debug tools as well. So eBPF puts a lot of work into verifying the code that it loads and to making sure that it only interacts with the kernel in a safe manner. So it is extremely difficult to break the kernel with incorrectly written BPF code. It might give you some nonsense values back, but it is unlikely to break the kernel. And that is what makes it so fundamental to various types of server analysis, because you can then add very, very low level complicated probes inject them right into the heart of a running kernel on a server and expect the server to survive the process. Whereas trying to dynamically load a kernel module that you've just written and has not been fully debugged yet into a running server and expecting the server to survive that and the module unload is much less likely. So that's why eBPF is a really clear benefit in servers where compiling the kernel is not a norm. And it would come up in distros as well, potentially. If you're working in any environment where compiling the kernel is not the norm, eBPF can be a very useful technique to grub around in the guts of the kernel and discover information sources. But in the embedded space, it's always going to compete with just compile a new kernel. And so while there are some cases where it would make sense, overall, it's a harder sell, except the other thing that happens with eBPF is that other people can write tools as well, right? So it allows people to write tools that reach into the kernel and discover information sources. It also allows people to write those tools and share them with other people. And that's where it starts to make sense, because now you have a language that people can write performance monitoring tools and then share them. And so there is starting to become a corpus, particularly around the BCC areas. So BCC was a BPF compiler collection. It was one of the original tool sets that came about to help eBPF. And alongside that, lots of the tools that were written in the original BCC scripting languages have been switched over to use the most recent BPF tooling, which are much more deployable than the previous ones. And they can allow you to write custom profilers. So that's the key thing about eBPF, is it's not just for you. You might well be able to find that other people have written useful tools, or if you write useful tools as a vendor to study your specific device, you can share them with your customers. It's, again, very good for remote diagnostics, because the customer doesn't have to have a great deal of sophisticated expertise to run these kind of tools if you've developed them. Okay, so next story. My board just stopped. It was running fine and then it stopped. No console messages. Can't see anything in the demessage buffer. It's just dead. It won't talk to me. The scope, obviously, of a board that just stops dead is very wide. We have absolutely no idea why the machine has stopped talking to us. For now, we're going to assume that the hardware has not broken. I joked about embedded developers, or at least not very good embedded developers, tend to blame the hardware as soon as they can. I have a very strong view about blaming the hardware, which is you can't blame the hardware until you've proven it. But for now, we're not even going to assume that it's not running. We're going to assume that it's reliable in terms of the memory is robust, and we've not got any kind of bus lockup. Bus lockups are curious because technically they're caused by software hitting bad addresses. But we're going to assume we haven't got that particular scenario at the moment, because it's a more difficult thing for us to talk about. We'll touch on that. We won't ignore it completely. So the details of the story, anything related to this stopping dead, can be extremely device specific. We're probably looking at either a deadlock in a driver or a bus lockup or things like that. So the board state, bus health, power state, we do not know. We do not know what state the board is in. It could simply have decided to turn off its own regulator. That does happen. So we have to understand how various debug tools work in this position, because the board is somewhat injured. It has stopped. We don't know why. We don't know what state it's in. So one of the things we can do with debug tools is if we understand how they work, then when they stop working, that itself tells us something about the system that we can use for reasoning. So a couple of initial analysis and truisms. Firstly, fail early. So everything I said about fail early can be applied to this situation. If we're guessing that we've come to some kind of deadlock, let's start with this theory. So I told you that print K is very robust. If somebody is calling print K, it will almost always issue the print K. So we have this theory, print K is robust. That probably means that if it's not talking to us, if the board has stopped dead, then presumably nobody is calling print K anymore. So what can we do to try and encourage things to talk to us and show us what's going on? So first off, if the board has stopped during boot, then you want to turn on early con, which is a mechanism to allow the print K to serial port stuff to activate earlier in the system than usual. Turn on early con. Also turn on init call debug, which will go through every kernel init function and tell you that it's running. So if you have a driver whose probe is causing your system to stop dead, then init call debug will tell you which driver is being probed at that moment. If you have any suspicion that clocks are involved, so what will happen usually in that situation is you end up in a function called clock disable unused, and which happens just after the driver probes, and the system can stop dead. The reason that usually happens is there is a critically important clock, like CPU clock, memory clock, things like that, that the clock subsystem has incorrectly decided need to be turned off. So it's something that was established by the bootloader, but that has for some reason not been marked as used during the driver probes. Then a way to examine that and study it better is to set this thing called clock ignore unused on the kernel command line. And at that point, the unused clocks will no longer be turned off, and the system is likely to survive to allow you to figure out which clock has stopped and why by looking at debugfs at the clock subsystem. At the very least, you should be looking at turning on things like debug mutex, lockup detector. Debug atomic sleep should be in this list as well, to be honest. I don't know why it's not actually. So debug atomic sleep should be in this list. You could even think about reintroducing something called debug spin lock. So debug spin lock was a really, really simple debug tool that basically added a timeout to spin lock waits. And so if you spent more than 5 seconds trying to get a spin lock, it would print a message to the console. The reason it was removed is because on massive multi-way SFP systems, hundreds of cores, it's not wrong to be stuck for 5 seconds waiting for a spin lock if something's really contended. And so there was no way to set the correct timeout, and it just caused lots of false positive reports from Big Iron. If you're not working on Big Iron, if you're working on a small embedded system, finding the patch that took that away and reintroducing it to kernel means that if you get stuck on a spin lock, you can arrange for a print K to be called when you hit it. So it allows you to be more production-y, ultimately. Debug spin lock was a relatively production-safe, low overhead tool because it only burned CPU cycles when you're already stuck waiting for a spin lock. It did make the spin lock code slightly less efficient though, so it did have a cost. The other trick that does come up is one of the reasons you can stop dead is getting wedged in an interrupt handler. So you're constantly whizzing around an interrupt handler, and we're claiming that we've serviced it, which makes the interrupt subsystem happy, but we never actually cause the flag to go down, which means nothing ever prints. We just keep going in and out and out and out. One simple, cheap way to find out if that's happening is to add a rate limited print into the GIC driver itself to print the interrupt number that it's trying to service. The reason we do it rate limited is to try and keep the system running. So what will happen then is you'll get 10 prints, and then it will hit the rate limiter, and the system will run cleanly for 5 seconds, and then we'll rate limited print. So it's bursty. It won't work in all systems, but the benefit of it is if you can then reproduce the problem, then every 5 seconds, it will show you the interrupt number that's causing you the trouble. So it's a very neat trick for failing early if you think you might be stuck servicing an interrupt. The other elephant in the room at this point is the JTAG debugger. If a board stops dead and you have a JTAG debugger, the JTAG debugger is always, always, always the best tool to figure out what's happened. The reason we don't talk about JTAG debuggers very often is because a lot of embedded developers don't have ready access to JTAG debuggers. Self-hosted debug is so pervasive in Linux that a lot of Linux developers, particularly if you've got a lot of boards, don't know how to fire up a JTAG debugger on some of the boards. And in some outfits, the JTAG debugger is this expensive, exotic bit of equipment that lives in a cupboard only 3 people know how to use. And the overhead of bringing it out is considered to be high. But if you're facing a dead board, a JTAG debugger is almost certain to show you where you've come from. It can still be confused by various bus lockups, but overall, a JTAG debugger is the very, very best tool to tell you what's going on the system. So if you have one, connect one. in terms of knowing how to use your JTAG debugger well, it is very, very useful to figure out how you can use your JTAG debugger to extract the dmessage and ftrace buffers from the target, because that allows you to run with the UR off, gather your trace information while you're running, hit the problem, hit the JTAG debugger, and then extract the evidence of what's gone wrong through the debugger. So if you have one, use one. We don't talk about debuggers very much in this course. Like I said, I am a KGB maintainer. I do believe in stop the world debuggers, but this course is all about trying to show you debugging beyond the scope of stopping the world and running a debugger. But for this use case, if you have JTAG debugger, get a JTAG debugger. Another aside is about SOC level debug. So almost all those self-hosted Linux debug tools are software based, and bus hangs stop software from running. They even interfere with JTAG debuggers to some extent, because as soon as you get the JTAG debugger to access the bus and it hangs up, the JTAG debugger fails as well. So there are things you can consider from a SOC point of view. The first one is non-CPU bus initiators. So if you have non-CPU bus initiators, things like DMA that copies the screen, keeps the screen running on your LCD panel, anything like that, they can provide clues about which parts of the bus are still running. Buses are not really buses in any meaningful sense any longer. They're actually trees and networks. And so you can have sub-networks in the tree that have failed and other paths that are working. So for example, if you can see the image on your LCD panel that's connected to your DDR, you know the bus route from the LCD panel to the DDR controller is still working. It means the RAM is working. That's great. You can even have controllable non-CPU bus initiators. If you have built-in coprocessors, anything that offers some kind of serial port to interact with the rest of the world, you can use that to do peek and poke. You can do that to probe different parts of the bus and find out if it's still alive. Off topic entirely, but Linux can also return that favor. You should absolutely make for sure that if your coprocessor is capable of crashing, that Linux is capable of detecting it and giving a core dump to you so you can hand it to your coprocessor engineers. That's completely out of scope for Linux debugging because your coprocessor quite often runs a real-time operating system. But if you have coprocessors in your system, you must ensure that Linux can core dump them so that you can provide post-mortem analysis for your coprocessor engineers. Post-reset memory recovery. We talked about a little bit about this with the KDump crash stuff. So with a little bit of hacking, you can usually get things like trace tools to target on-chip SRAM, which is nice because it's usually very, very fast. You can get tracing tools to track uncached RAM, but that is usually very, very expensive. So the problem with post-reset memory recovery is the contents of the caches get destroyed. So you end up having to add cache flushes into your tracing code, and it can be a little more difficult to integrate. But nevertheless, if you have access to post-reset memory recovery, it's there. And finally, this is another thing I can literally only tell you about. And if I knew the answers, I'd almost certainly be under NDA to not tell you anyway. But many, many SOCs contain registers to help you diagnose bus hangs. Bus health, speeds at different nodes. There's basically information quite often in registers within the SOC. They are also quite often secret, which means I couldn't tell you about this. You would have to ask either your vendor, or if you are the vendor, ask your hardware team. They don't always exist, but there are definitely registers there. The reason they're kept secret is because none of the vendors want to have to cope with supporting people who have broke their system at such a fundamental level. The idea is that once you've got access to those registers, you can try overclocking a corner of the bus, and then they're just looking at horrendously complex debug scenarios that they know to be impossible because they set the bus up a particular way. So that's the reason they tend to be kept, it's not really secret, but they don't like to document these things because they don't want to see fundamental changes to how the bus works, because it's been designed to work that way, it's been tuned to work that way, and during verification, if there have been any bugs, it's working around bugs that they know about and they don't want you to rediscover them. So moving away from those things a little bit, ftrace. Ftrace would have written to memory the name of the function that was running just before the board failed. That'd be really helpful. The problem for this is the same as with the post-reset memory recovery, that the caches will cause problems with it. So RAM does survive a reset if you get the refresh running fast enough. And the problem is that the caches are sufficiently large and get destroyed. So if you have any kind of bus initiator you use that's cache coherent, JTAG debuggers are usually cache coherent. Some of the bus initiators that are under software control may be cache coherent. You could use those to suck out an ftrace buffer from a failed machine. But ultimately, we have to find a way to store the trace where we might find it later. And that brings us to a thing called RAM-oops, which can be very useful. So RAM-oops is a generalized framework to store logs in persistent RAM. Persistent RAM is system dependent. The classic implementations are basically a reserved chunk of memory and a bootloader that reprograms the SDRAM, the DDR refresh fast enough so that the contents are preserved during a power on reset. If you stab the reset button, the refreshes are established sufficiently early in the bootloader that we don't lose the contents of RAM. So we provide it as a selection of arguments for boot up. And the reason I mention the caching here is that ftrace, we can have ftrace buffers in our RAM-oops space. Fully fledged function tracing can introduce massive performance degradation when you're writing into uncached memory. And we took some of the Hackbench tests to prove this, and on a particular I can't tell you which particular platform it was. It would have been one of the 96 boards. A particular platform, one of my team observed that we could change the performance of Hackbench by several orders of magnitude, 1 second to 120 seconds. That doesn't mean you can't use it. That means you have to have a laser-like focused on what you record. You can't do pervasive system-wide tests, but you can do, you could look at maybe just the scheduler trace points, which would give you the name of the thread that was dead. You could even subset the trace points, so you literally only get the switch. And if you just get the switch, again, you've got the name of the thread that's causing trouble. Somebody's asked a question about multi-core socks. In principle, yes. So somebody said, if you've got an SMP system, can you try and run 2 kernels and use one to debug the other? I'm slightly skeptical because if you're looking at really tough things, they'll be sharing a bus initiator. So when one fails, the whole cluster will fail because it all goes out for the same L2 cache. So yes, in principle, it can be done, although bootloading the second kernel is quite hard. Yeah, it's not something I would personally have invested the time to build, even if I was working at the SOC vendor. Bear in mind that SOC vendors can spend longer building these kind of things than OEMs or people like myself at Linaro because they get to use them for the next 5 years. So some of those sophisticated vendor tools can be built, but as a vendor, I would always preferred to find a coprocessor to do that kind of thing for me. If you do want to play with partitioning the cores and things like that, then there's a jailhouse hypervisor is probably the thing to look at. That's a partitioning hypervisor that allows you to split out the cores in a relatively same way. Okay, so we've got our targeted trace in our RAM-oops, and then there's just a thing on the right here that shows you how to recover it and look at it after the fact. Since we're talking about oops, how long have we got on this? Yeah, okay. Just checking I'm going to have enough time to come through this, but I think I have. So having talked about RAM-oops, one of the things that is quite often stored in the RAM-oops is the oops. That's the original purpose it was there for, so that you can store the oops there, reboot, and examine what's happened. There's a lot of information in oops traces. You don't necessarily have to read it all. But the basics, I mean, clearly you get the first line that gives you some clues. Some of these are more helpfully written than others. They tend to describe the actual hardware fault that happened. So unable to handle kernel null pointer reference is very nice, and you get an address. Some of the things that you get on some kernels, like data abort at, is a slightly less intuitive understanding because it's based on, this is what DABT stands for, data abort, is because it's using the hardware phraseology from the manual. So if you get phrasing up here that you don't understand, it's probably come straight from the architecture manual, and you can look it up in there. Having talked about virtual addresses, it does tell us what type of pages we have. You can see here 4K pages with 48-bit virtual addresses. 48-bit virtual addresses means that you expect the top 16 bits to be F if it's a kernel address. That's what a 48-bit virtual address means. It means the bottom 48 bits change, and the top 48 bits are going to be all the same, unless you've got top byte ignore going. So when I've said you need to know what the memory layout is, that is the information that lets you check that the kernel you've got back from somebody else is the one you expect. It doesn't matter too much if you can remember what PGD, PUD, PMD stands for. There, D is directory, P is page. I forget. I think it's middle, upper, and I can't remember the G. It doesn't matter too much if you remember these or even follow the addresses. The key information is the size of the virtual address so that you can read things. You'll have some reminders about what modules are involved. That may be important, but in general, it's just noise. Tainted can be useful. So everybody remembers tainting as the thing that comes in when you load a non-GPL module. But there are actually multiple taints. There are taints to say we've ever had a soft lockup. There are taints to say that somebody force loaded a module instead of regularly loading a module. So that's loading against the advice of the module loader. There are other reasons to have taints. So if you see taints, you'll get a flag name. You should look up that flag name and find out what's happened, because it might well be that sometime way before you ever got to look at the oops, that was actually the genesis of the problem. And then you move out into the actual addresses and crashes and so on. So the kernel will be looking up symbols at this point because, particularly with address space layout representation, the actual program counter will vary depending on which time you rebooted, but the offset into the sysrec will not. So you get the sysrec plus OX120, for example. If you want to convert those on a kernel with debug information to a line number, which I think is one of the questions we had earlier, there's a couple of ways you can do it. One is to use GDB without connecting to anything. So GDB allows you to interact with the symbol table without connecting to the target. So in this case, we've decided to work on VM Linux. We haven't connected to the target, but we can list and disassemble the functions that we're working in. So we can list this particular address, find out what's going on. We can disassemble it. We can. The disassembly is quite useful because it intersperses the C and the assembler to some extent to help you understand how the code is structured. You can also use things like addr to line, which allows you to take a address, or in this case, for some reason, we've taken the stack pointer address, which is quirky. This one doesn't give an offset, so it's the offsets that are most useful. I think there is a way to use an offset with addr to line, but again, it allows you to take these things and try and map them back to C in various techniques. Like I said, I always reach for GDB. Because of my history with GDB, that's the tool that fits my hand best. Addr to line is very popular, particularly for writing tools to analyze other things. But yes, when you've got address-based layout randomization and a hard pointer, it won't necessarily give you the right thing. The other thing that is worth knowing to understand oops traces is the procedure call standard. So what's basically happening in a procedure call is these bottom registers, on the case of ARM64 X7 to X0, is that the first arguments will be put in X0, the second argument put in X1, third argument X2. So once you've got the entry point to a function and a little bit of disassembly knowledge, you can figure out what the arguments were to that function. With a little bit of care, you have to be able to read enough assembly to see if it's copied or overwritten the argument. But in general, you can work from this and if the number here is small, basically, if we're near the beginning of a function, you can figure out what the function was called with, and that will usually show you, particularly when you've got nulls in x0 and x1. If you imagine that a lot of the kernel has context pointers to point to the device structure in x0, x1, particularly if you see nulls or anything that's not f's, that can be a sign that the pointer that you've been handed is just rubbish. So to go into a bit more detail on that, the procedure call standard, this is the ARM32 procedure call standard. In the case of ARM32, there are only actually 4 parameter registers, and after that it spills over to the stack. So you can discover the first 4 registers by them being stored in here. Again, you then have to look through the code a little bit to see if R1 and R3 are being, R0 through R3 are being used for any other purpose. But in general, early on in a function, they will be left untouched. You can see what they are. Stack pointer is R13, but it will get presented to you as stack pointer in the stack trace. Again, you want to look to see that that is the sort of pointer that you expect. If you've got VMAP stack on, it should be in vmalloc area. If you've not got VMAP stack on, it should be in the regular kernel mapping. Link register is the other one that crops up a lot. So when you make a function call, particularly through a pointer, if you go to a bad function pointer, the program counter will be garbage, but it will crash almost as soon as you jump to the garbage program counter, and the link register will contain the place you jumped from. So when you see a good link register and a bad program counter, that's usually an indicator that you followed a bad function pointer. So you can go back to look at the link register, look up that, and you'll find out which part of what subsystem is following the bad function pointer. And if you're really lucky, you'll find out which the bad function pointer is, in what register the bad function pointer is being stored, and then you can start working your way back from there. Exactly the same process on ARM64. There's just more registers. There are more additional registers involved in these processes, so that if you get extremely good at reading ARM assembler, you can start using some of the other registers. But the key thing, and the thing that I really want to make clear, is that you do not need any significant assembler experience to have a shot at trying to figure out what's in R0 through R7. And particularly if you're doing something like taking an OOPS trace from a customer and trying to get as much value from it as possible because it's hard to reproduce, then it's worth investing the time to say, right, so I'm in this function, yep, those registers haven't been touched. That means that R0 is still the first argument of this function. Does it look valid? You can do that kind of thing quite easily from stack traces. So this is a worked example. It's not the best worked example because in our case, we've got this value called key, which we know is not a pointer. The value looks okay. It seems a reasonable key to have. And in any case, key is unused in this function. So it's an example that shows you we're into this sysrec to handle crash. So this is basically a sysrec that requests you crash so you can test the stack trace machinery. But we've got a quick summary of what we've looked at. You know, we can see that we've already made a jump within the function itself. Once you've entered a function, when you get things in the link register that's its own function, that's basically a previous function call, and that's the return. That's the last point at which we return successfully into the current function. So in other words, we called RCU read unlock, we returned from RCU read unlock, and as a result of that, the link register ended up with the address we jumped back to after RCU read unlock. And we can look at the arguments, we can find out that this is a 1 and so on and so forth. One thing that is worth mentioning, somebody said, how do you find things back to C? There is a script that can help you. So you can do it by hand. You can use GDB, as I showed you before. You can also use this script called decode stack trace, which will basically take an OOPS and convert all these pluses into function, file name, line number, which again, really is a big jump to get you back into C very quickly. So there was a question from one of the audience earlier. I think that's the answer that I was working towards at that point. Final thing that can be done is converting binary code into instructions. So some of the OOPS handlers will actually show you a small chunk of memory just around the program counter. So first off, if it's static code, if it's not had any dynamic modifications to it, we can just reach in and disassemble the code and look at it. The other thing we can do, at the end of the stack trace, we've got code, and then the bad opcode. So this is basically the instructions the machine was running before the oops. And the kernel does not contain a disassembler built in. So it is just showing you raw code. But you can take these steps or write a script to take these steps that will take those opcodes, assemble them, produce them in an object, and then you can fire a disassembler at it. And you can check, for example, that the code there is the same as the code you see in your disassembler, i.e. that the code has not been corrupted. You know, if you're worried that memory reads are not reliable, being able to prove that the opcodes have not been read reliably is a huge way towards blaming the hardware with actual proof. It's not that blaming the hardware is wrong, it's that you have to be able to prove it. So moving on from that, I'm aware I've got 15 minutes left. Core site can still be our friend. So bear in mind that we've been along the longer side about oopses now. The story we had was your border just stopped dead. And I think there was a question about using SMP to look at other cores. So there are some other things we can do to make SMP more useful in finding out what's going wrong in these systems. Core site offers one of these opportunities. First off, you've got core site trace. Core site trace is even more powerful than JTAG. So if you have an off-device tracer in the cupboard, finding the person in the company who knows how to use the tracing box and offering to be nice to them if they help you for a bit. Yeah, do a deal with that person. Get them to set up the core site trace unit for you and find out what's going on. But if you don't have that piece of hardware, there is still a final trick that you can deploy, which is that those embedded trace macro cells store in their own register set the last PC that we jumped to before we failed. So in other words, it's a PC that shows us the basic block we are executing at the point the CPU jammed. So any device in the system, because the ETMs are bus accessible, you can't read the program counter from a stuck chip because the only place that register is stored is accessible to the core itself. But you can read the ETM for the same core on the bus. So in other words, we can read out that program counter of the last accessed place. You could read it from coprocessors that have access to the bus. There's also this feature in the kernel, which was written by one of my team, core site CPU debug. This can basically be attached to things like the lockup detector or even RCU detect, and it will extract the last program counter that the partner cores are running. So in other words, when we detect that something's gone wrong from a surviving core, we can reach into the ETM of the failing core and get information about what basic block it was executing. So in this case, you can see that for some reason it's jammed in handle IPI. Now that was probably something we did synthetically to force this. So that's a really good answer to the question about side-by-side. Oh, something correction. Oh yes, that's true. Yes, I've forgotten that. So I've been saying it's the ETM that stores the last program counter. It's not. It's the intimate debug unit for the peripheral, but that's also memory mapped, and it allows us to extract the previous program counter. Thank you. So that was a nice way to exploit SMP a little bit without having to go to the trouble of a second SMP core to watch things. Okay, so I should go through this one fairly quickly because this is actually quite a well-defined story. I'm sure this used to work. A couple of weeks ago, I ran a test, and then I came back a couple of weeks later, and it's no longer working. So this is actually quite narrow. We do know how to reproduce the original test that failed. There is one subtle thing here. The reporter sounds like they've been a bit ad hoc, so they may not have got really good records about what they were keeping. So we're assuming the kernel source control is very well controlled. When we say we can go back 2 weeks, we can go back 2 weeks and it will be correct. Other parameters are often less well controlled. It's not that uncommon for people to change their kernel configuration and forget they did it. And then the reason they've changed is not because the code has changed, it's because they enabled a particular kernel feature a week ago and forgot about it. Even more than that, it's really easy to forget that you upgraded your compiler and that you're actually looking at a difference in behavior between compilers, or that you've rebuilt your user space. So one aspect of this is that you ideally want to be able to go back a couple of weeks and reproduce the success before you try and study the failure. If you can't reproduce the success from a couple of weeks ago, then you will have to be thinking about the other variables that have been involved. Kernel configuration is a really obvious one. Record the broken one, look for the right one. Kernel compiler and toolset, again, you know if you've changed compiler, but you can forget about it easily, and so on. So, I mean, git bisect is the first tool I think will spring to most people's minds at this point. This allows us to start from a bad kernel, label a good kernel, and then bisect the history, trying to find out what went wrong. I would very, very, very strongly advise people to have git bisect run and a shell script. Don't mess about with git bisect good and git bisect bad. The reason for that is because you are human, and it's so easy to double tap through the command line history and pick bad when you meant good, and then the whole of your bisect is wasted and you don't know where it failed. A much better approach is to have a shell script to drive it for you based on the return values. So the return values that it can provide to guide bisect are the kernel compiled and everything's good, the kernel compiled and the test is bad, and there's this special one called kernel failed to compile and test can't run. So in other words, you can have a third state. There is good, there is bad, and there is I cannot give you a verdict. So for example, if I'm doing KGDB regression testing, I will build a kernel and I will then do a no-op action on KGDB. And if it won't start, I can't then run the test case I have and I return 125, for example. You may think, oh, I've got real hardware and it's really hard to write a working kernel compile and test. Write it anyway, write it anyway. The key thing is, yes, if you've got real hardware and you haven't got a bank of relays to press buttons for you, then there may be a manual step required to do the bisect. It may be that you need to robotically press a few things, press the reset button, press a flash thing, press the reset button again. There might be some manual steps. Get the shell script to prompt you to do those, and then let the shell script collect the verdict. Because then you won't make mistakes. You can probably, if you carefully set this up with a bell and everything else, find a textbook that you've been meaning to read for a couple of months and get the machine to do all the work. And you just basically try and do something else, but active enough that when it says, I need your attention, you can provide it your attention for a bit, do the manual step and move on again. It just stops you bisecting in the wrong direction. There is nothing more frustrating than spending a day and a half doing a manual bisect and be told that the output is unclear and not being sure if it's your fault or not. Unclear bisects do happen. Sometimes verdicts aren't 100% stable. But not knowing at the end of a day and a half if it's your fault or you should start again is a real problem. And there are techniques you can use with bisect to replay things and look at the previous versions, but having the run, because if it goes wrong, you've still got to work through each of the steps from previous, even from the log. If you're replaying the log and trying to copy bits from it, so I have seen the comment on that, you've still got to run the actual tests again and the builds again. And so you can find out if you went wrong by running it twice and comparing the logs. But if it takes a day and a half, running it twice and comparing the two logs is still now a day and a half where you didn't know if you'd done it right or not in the first place. So I strongly favor avoiding human error. If there's a statistical issue, if the test isn't 100% reliable, there is actually a newly added feature to Git called stochastic bisecting, which is not in this yet because it's really new. But there is an LWN article about it. So if you find bisect interesting, but you know that some of the tests you have are not 100% reproducers, there is this thing called stochastic bisect, which allows you to try and bisect when the tests aren't perfect. So it's really cool. Other things that can happen. So K-test. K-test is a Perl script. It sits in the kernel sources. It can be used automatically to run tests. So you can use it as a high-level framework for git bisect. The reason I like it is because it can bisect config files. So I mentioned that people might have not well versioned their config files. If you have a working config file and a broken config file, then K-test can drive tests to experimentally change config files to convert one to that and tell you which kconfig option it is that's causing the trouble. So that can be quite useful. It is not a well-documented tool. It also does make some assumptions about automation that can be a bit of a pain to meet. But if you can get it running, on your platform and write some notes about it so your colleagues can copy the idea later, it can be a very nice tool because of that capacity to bisect config files. And the final story, which I'm afraid I'll warn you before I go into it, is going to be a little bit anticlimactic, because this is the one that every embedded developer knows and dreads and would like there to be a long, complicated answer and a big set of tools. There isn't, I'll tell you that beforehand. Random failures. I wasn't doing anything special. My board just failed, no reason, system was busy. But all of the tests that I've run do pass sometimes, it's just sometimes they also fail. So the scope, I mean, this is very, very wide. The failure could be across the system. There are two things I suggest be taken as absolute truths. It is not a compiler bug until you can point to the bad opcode and explain why the compiler was forbidden to omit it. It's as simple as that. The compiler is a nice reproducible tool. It always generates the same assembler from the same C, except in some very extreme circumstances. So until you can point out an opcode that the compiler has omitted that it was not permitted to, it's not a compiler bug, it's probably a bug in your code that doesn't treat the optimizer correctly. Likewise, it's not a hardware bug until you have proved it. You can reduce that to powerful evidence. I mean, proving things is quite difficult, but you can have stuff in the logs that provides strong evidence that there are difficult, it's not easy to explain how these two observations could be made without it being a hardware bug. That basically gives you evidence that you can start discussing things with hardware engineers, but without evidence of specific logs and it's the specificity of the evidence that's really important. It's not saying, well, we just changed a whole bunch of things and now it must be the hardware. That's never going to allow the hardware engineers to take part in the debugging activity. Related notes, there's a lot of problem solving to be done, but some of it's not really kernel debug. A lot of it is going to be hardware debug. Kernel engineers, by their nature, are going to be exposed to weakly validated hardware, especially commodity interfaces that are too complex for your validation team to look at, things like PCIe and Wi-Fi especially. The other thing that's difficult with the hardware bug aspect is SMP race conditions and memory corruptions are quite difficult to distinguish from each other. So I'm afraid, I warned you anticlimactic, there's no real trickery here. You're just going to have to do a certain amount of work. But we can divide the work into investment that you make ahead of time to allow us to be more comfortable when these problems rear their heads, things that you can put into your project plan, things you can advocate to your management. And there are things on the right that are techniques that you use when they apply. So kernel drivers, bootloaders, whatever else you have should display the concept of every possible reset reason register you can find. So that when your board just fails randomly, the first thing you can do for the bootloader is rapidly say, that was an overheat, that was a watchdog, that was a brownout. Particularly anything related to power can be a strong risk. It follows, therefore, that anything related to power needs to have nice trace points that allow you to be tracing their activity and disable them if needs be. The system is at its most vulnerable during dynamic voltage frequency shifting, because we're doing a voltage shift, we're waiting for the power supplies to stabilize. If we start drawing power before things are stabilized, you get a small brownout with a random chance of crashing. It's one of the highest risk things we do to manipulate the hardware. So you should always make sure that they can be traced and disabled. It doesn't mean that you disable power management, it's somebody else's problem. I do know companies where, so people just turn off the power management and then say, all right, well, the power management engineers will fix it now. I don't think that's a healthy way to allocate blame in these circumstances, but nevertheless, being able to disable this component is a good thing to do. Having a P-store driver so you can have RAM oops, that's definitely worth doing ahead of time. This one's just facetious, but knowing how not to write SMP bugs can be quite helpful. Training, I suppose you call that advocating for training, making sure that your engineers know the hazards related to some of this stuff. And of course, automating everything you can automate, you can produce, you can gather statistical evidence once you've automated of how frequently it happens. You can make small changes and you can see if it affects the statistical outcome. When you're doing ad hoc manual testing, it's almost impossible to generate useful statistics. On the other side, when problems appear, the single most important thing is to maintain a high quality log that summarizes the investigation. Once you've gone on a couple of days and your manager's starting to say, how expensive is this going to be? How long are we going to do? When will we have it fixed? Your logbook is what allows you to demonstrate that work has happened, even if outcome has not been reached. It also is what allows you to summarize the evidence such that you can bring in other people, debug consultants, hardware engineers, whoever it's going to be. It allows you to bring them up to speed, let them reach the same level of reasoning you are, possibly suggest other ideas or other tools. Always replicate the same problem on a physically different sample with a physically different power supply, as in wall supply. You never ever want to waste your time believing it's a software bug when you know that these things change board to board. Once you've changed board to board, it doesn't mean you're home free, because there are technologies like voltage tables in the CPU that give you operating points that are different on different physical samples. So it doesn't mean that you're free of bugs just because it reproduces on it doesn't reproduce on a different board, but it's vitally important information to know if it reproduces on different boards with different power supplies. All of the failing early techniques that we discussed at the beginning of today's talk should be covered. Memory tests can be useful at this point. There is a risk that you haven't configured the memory timings exactly perfectly and it fails on very rare occasions. The kernel boot time memory test isn't very good for testing. It does a quick sanity test of addresses, but it doesn't actually go looking for trouble in the bus subsystems and all the various communication systems that go on their way to memory. An always on test that runs in user space or a coprocessor is a much better way to try and prove that the RAM is working. And a failing memory test is the smoking gun that allows you to go and talk to hardware engineers and say, look, this memory test has failed. It should not do that. I think the memory timings are wrong. That's the proof that you need to really help them. And it can take a long time. I mean, I've worked on projects where we started these memory tests based on some partial evidence we had, and it still took 3 weeks of runtime before we got a smoking gun. But we did eventually get the smoking gun off an always on memory test, and that was enough to get the memory retimed, and a month later everything was fixed. Core dumps were the other aspect where it can be useful to prove hardware do not act correctly. So, for example, I have worked on core dumps where you could observe the opcode, you could observe the register state and say that it's impossible for the machine to have executed that opcode and result in that register state, which meant ultimately the iCache fetch had fetched a different instruction. But there's no way to observe that directly, but you can observe it by seeing that an instruction has not done what it was instructed to do. This is the last technical slide. I'm slightly overrun. I apologize for that, but I am going to complete the aspect of it. This is part of not writing SMP memory bugs, and certainly not writing, this is not actually SMP memory bugs. This is another type of memory barrier that helps you write correct actions on drivers. So our architecture has a weak memory model, which means that when you write memory map to peripherals, there are certain orderings that are not guaranteed. In particular, if you are writing to two peripherals, for example, a peripheral that uses DMA and a peripheral that is the DMA unit, the ordering of the writes to the two units is not guaranteed. So in other words, it is quite possible if you write to those two units that the writes to the DMA engine will happen before the write of the DMA descriptor to RAM. So it's very, very important to get these things in the right direction. So the default accessors, write L, read L, IO read, IO write, will give you strong memory ordering by internally containing memory barrier instructions. So if you use those instructions on anything that uses DMA, you should not get memory problems. The problem comes in because things like write or read or relaxed are starting to soak into the culture as faster ways to access registers, which is true. They are faster ways to access registers, and they can happen so fast that they don't appear in the right order. The reason they are fast is because they do not contain any code to ensure they act in observed order. So if you have code that has started to use these things, it needs a lot of review. It needs to be reviewed by people who understand the precise details of memory ordering, and whether you need to read back registers or rely, or you can rely on memory barriers and all these kind of things. Will Deacon has a fantastic talk at ELCE 2018, I think, that goes into this for a full 45 minutes. I can't go into details now, but particularly when you have got people who are using these accessors on anything that does DMA, you need to be sure that the person who's written it or the person who's reviewed it has had the ordering with which things can happen in mind when they wrote it, because if they haven't, it's a very high risk area. So that gets us to the end of the stories. There is a wrap up coming up. First off, we've run this from Linaro Developer Services. We're a contracting and training company. We've given you a full module from our training program today. So this is not something we've abridged or set up for the webinar. This is the first module from our advanced kernel debugging course. We have a variety of things we can do. We work with, as contractors, we can do certain meetouts of consultancy. And the thing that makes me come to work a lot of the days is to get training done. I'm the training manager at Linaro. We have a number of courses. We have just put the training catalog online as a download with no click-throughs, no registers, no give me your email. So if you're interested in what else we can do, you can go straight to our website, Linaro Training search engine, and you will find our training catalog, and you will find this course or this module that you've seen today as the first module in one of our courses. But like I said, we didn't want to just give you a teaser. We picked the first module, we picked the most general module, the one that does stand alone, and I don't think we've sold you short by not giving you the rest of the course. The rest of the course is awesome, but we've not sold you short. And finally, the other thing that I'm involved in personally is the technical support component of Linaro. We call ourselves developer technical support. We're here for engineers who are having trouble with kernel, with certain boards, lots and lots of different subjects related to Linaro. If you are a Linaro member company, you likely have permission to use Linaro Developer Technical Support already. It is something we can also add to any of our engineering contracts. So if we do engineering on your behalf as contractors, we can back up what we do with technical support. And the free gift, I have to come to the free gift, which I said we would give you. I'm about to copy the free gift into the shared folder for the course. And it's basically a word cloud based on almost every technical thing I have mentioned today. You can even see KGDB and KDB in this corner here. So some of them bigger than others. It was partly based on word frequency and partly based on amplifying a few aspects of importance. Perf is slightly oversized, and perf is not the most important debug tool there is. The idea behind this is it's a post that you could print, you could put it on your office wall, and when you're staring into the abyss, when you can't remember what I said in this presentation, you want some trigger to try and find the many, many tools that we've talked about over the last 2.5 hours. There are a lot of them, right? So if you want some memory trigger to try and help you find the first word, and then from there, either trigger your own memory of what I've been saying or to do research online to try and find things, this is a poster that tries to let you try and find things that you might not have thought of. So it's there if you want it, it's not there if you don't want it. And the final thing that is an option for you is the lab sessions. So like I say, we've copied this directly from one of our courses, so we've maintained the lab sessions as well. The lab sessions only cover tools that we do not have other modules to describe. So we're going into things like dynamic debug and init-call debug and some of the various things that are one-offs. We just tell people about them, and we expect them to be able to go from what we've told them in today's course without any additional pieces. If you were to do one thing that's not in the labs, I would recommend starting up ftrace. So that's not in the labs because we have a whole module on ftrace. But if you're not taking that module, that's fine. But if you do one other thing beyond the scope of these labs, fire up ftrace. You can do it with all the tools we've given you. So we've offered a open embedded based SDK that gives you a easy to run QEMU system, which you just fire off with this command once you've got everything else set up. It allows you to put in a custom kernel. You can have that custom kernel with ftrace. You can use ftrace to go and examine the virtual machine when it's running. You can also, of course, run it on your own machines if you have machines that you run more separately. So the whole of the exercise in this course, although we've presented them to you running it in a virtual machine, if you have a kernel and a machine that you use frequently, all the ideas, turning on dynamic debug, turning on ftrace, turning on init-core debug, you can all do on your own board as well. There is no need. We've got all the downloadable content if you want to work exactly in the environment we've provided for experimental purposes, but you don't have to. You can work on your own boards. That will give you the same learning experience, if you like. So the labs are there if you would like to do them. Other than that, I'm sorry for the extra 10 minutes. But yes, I'm at the end. I'm happy to, if there are any sort of final questions or things that I've missed or things that I didn't cover as deeply as you would have liked, I can talk about them if there's any questions coming up. But if I don't get any questions coming up, then I shall sign off. I'm talking very slowly now because I've got to leave it 10 seconds to give you a chance to type in. But no, I don't see anything else coming in. So yeah, I hope you've enjoyed it. Like I say, I like giving this course. It's one I'm very happy to do to a big audience. So yes, I hope you've enjoyed it, and